Welcome back to Computer Vision. This lesson is going to start a whole unit on motion. Now, in the real world, things really move. You know, trees blow in the wind, boats move along the water, a baseball player swings his bat and typically misses if he plays for the Mets. But, you know, things are moving all the time, and our perception system handles them. In computer vision, we also want to deal with motion, but what's kind of cool is actually nothing is moving. What you're seeing here is a repeated GIF image, and I've made it sort of coarsely sampled, actually from some slides stolen from some folks listed below, so that you can see that it's actually a sequence of static frames, okay? And, you know, of course, the issue is that when we look at them, when they're not so separated in time by quite so much, we see this nice motion. And what we would like is that the same perception of motion that we have, we'd like to be able to give a machine. We'd like a machine to be able to understand the notion of motion, if you will. So when we're going to talk about motion, here we're going to start talking about video. Now, really, we're just thinking about a sequence of frames, and in fact, a long time ago, we used to just call them sequences because a camera would go, and then a camera would take another picture, and then sometime later it would take another picture, and the question was how to use those. These days, of course, much more ubiquitous is a notion of video where a sequence is captured over time, usually relatively quickly, so things can't change a whole lot from one sequence sample to the next, and usually taken at regular intervals, whether it's every 30 hertz, 60 hertz, 24 hertz. The idea is that it's at regular intervals. Now our image is no longer a function of just space, x and y, but our image is a function of space, x, y, and time, t. So our signal is I of x, y, and t. But as I said before, sometimes when we describe them as a three-dimensional function like this, we tend to think of all three dimensions as being the same, but they're not. Space is quite different than time. So if I were wearing a nice checkered shirt instead of this gorgeous green, as I moved in space, you would see pixels changing very quickly in terms of their intensity or their color. But if I were to change the pixels that quickly in time, you would essentially see a mess. You would see all this flickering and things changing very rapidly. So in general, even though we think of these as a three-dimensional function, remember that time and space are different in terms of their statistics. Let's talk a little bit about the processing of video and some of the applications, or not just applications, but the general computations that we would want to do. And then we can talk about how motion can be used in order to, or the motion processing can be used to do that. So a simple one is background subtraction. So you might have a situation where you've got a static camera and the background is considered to be a static background, and I've got some object moving in the foreground. And my goal is to pull out the foreground object, the moving thing, from the static background, so I might be able to track it or model its dynamics or recognize it or something else that's focused on the object. Another interesting application might be what we call shot detection, and that's illustrated here. So the idea is here we have a bunch of frames that are in a video, and commercially produced video is usually made up of a sequence of shots, each shot coming from a particular camera. The camera might be moving, it might be panning, it might be dollying, moving, translating, and then you'll cut to a different shot. And in this particular case, our shot boundary is shown right here. Right? All of these are taken from one camera shot, and these are taken from another. Often, it looks to you like they're taken one right after another, but in reality, they changed everything. They moved the camera around, changed the actor, redid his makeup. He went and got a smoke or whatever it is they're smoking on set. And then they came back and they did the next shot, and they just cut them together. And if you think about what that would look like to a computer, in one case I might have a nice smooth background moving with some objects moving within it, and then there's this rapid change, and I might have another camera which might not be static, it might be moving as well, and the analysis of that motion might allow you to do the shot detection. So we have background subtraction, we have shot boundary detection. Maybe we have a bunch of objects that are moving in different ways within a scene, and we'd like to separate out each of those objects. And that's referred to as motion segmentation. Motion segmentation is you segment the video into multiple what we call coherently moving objects. All right, so they're each moving, but they're moving in an independent way. So here's an example. And what's funny is this is a static image of a snake and a mongoose taken off the web. And you could imagine trying to separate these out just spatially. In fact, you can sort of do that. But in fact, the color of the mongoose and the snake is very similar to the color of the background. And if you were to track these things, you would see pixels coming and going. But if you actually were to look at the motion, you would see the motion of the snake as being a coherent thing and the motion of the mongoose as being a coherent thing, and you would be able to use motion to help you segment out those objects. This notion of coherently moving objects actually comes from some very early work in vision that was done by the Gestalt psychologist. Gestalt psychology, which is really sort of the turn of, I was about to say the turn of the century, turn of the previous century, really around 1900 or so, is when they first started thinking about the types of processes of the brain does in terms of what actually has to be constructed, if you will. That is, what sort of processing does the brain have to do? Now, they didn't really have computational models yet, so it was very descriptive, but it really was the precursor to a lot of the computational stuff that we all do now. So one of the founders pictured here is Max Wertheimer, and if you read, it says that one of the things that really interested him was at a train station you could see a set of moving lights going, one, then another, then another, then another. And of course these lights would just come on, but he and everybody else saw it as moving, right? Saw these sequence of lights as motion. And this question was, how does that happen? What is the brain using? And he took a bunch of assistants who later went on to become also famous Gestalt psychologists. And they started looking at the way the human system groups things together. And they came up with a bunch of rules. So up here we have the not grouped, right? We just have a bunch of black dots. Well, it turns out that if you just move them a little bit, right, proximity will cause you to say, oh, I have 3 sets of 2 there. Likewise, appearance. So you see that there's black, white, black. All right. Similarity also in shape. So we've got horizontal ellipses and vertical ellipses. But one of the ones that they did that was kind of cool was called common fate. And you can see what common fate here means is that they're moving the same way. And then this got studied tremendously by all sorts of people doing work in psychophysics in trying to understand how far could a point move between 2 frames for you to see it moving. And then it turned out that there were actually different things. If you do it a very small amount, you actually see the point moving, right? You actually think that it went through all those little stages. And then if I put the point further away, it would be off and then on, you would get a sense of motion, but you didn't think you actually saw the point move. You would think it disappeared here and reappeared there. So you had this idea that something moved, but you didn't actually see the things moving. That was called a long-range process. I think these were done by Oliver Broddick, who was a famous psychophysicist. And so anyway, so this is this idea of how does the brain process such motion. Sometimes common fate is the only cue you have. So for example, I'm showing you a random dot image. You probably don't see very much there. What do you see? You see random dots. Good. All right, take it away. Yawn. Well, don't yawn, you'll go to sleep. All right, put up another one. There it is. Is that the same random dot image? You have no idea. Okay? But let me go to the next one. This is a GIF I made myself. I'm very happy. Now you're seeing 2 random dot images sequenced one right after the other. So what you're probably seeing is a square moving back and forth, right and left. All right? You probably see a pretty sharp boundary of that square. You actually think there's like an edge there. Well, let me stop it. No edge. Okay? That edge was manufactured in your head based upon the motion field. Okay? And our goal is to understand this computation of motion that would allow a system to say there's a boundary here based upon different motion. Something else that was observed about moving lights. So I'm showing you this picture and you probably don't see very much. So you probably don't know what this is. To me, it's obviously a horse jumping over a fence. Except when I put it in motion, oh, it's Megan strolling along. She has such a nice stroll. No, it's not. It's just some set of random dots from some other exhibit. Notice that that center point is fixed. It's not moving at all. And in fact, if I erase that and you look at that and you just stare at that point, the whole thing looks kind of weird. But then if you just stop looking at that point and just look at the whole thing, you see somebody moving. Except now I can't get that weird center point out of my head. All right? But the idea is that with this very impoverished stimulus, you're able to perceive not just motion. Remember, nothing is moving here. Right? There are no points moving on the screen. Point, point, point. You see them moving. Not only do you see points moving, you see a person moving. All there are static pictures of points. That's all that's there. The rest of what's going on is being manufactured in your head. And our goal, because we're computational vision people, is to think a little bit about how to get the computer to manufacture some of that information.
Can you find some interesting examples of impoverished motion from the web? Now these don't have to be videos of dots moving. They can be anything where you have very little to go by and yet your brain reconstructs and interprets the overall motion. Sometimes correctly, sometimes not. You can paste in links to web pages, videos, or papers. Now here's an old video from Cornell University. It shows how the same motion can be perceived differently in different scenarios. Fascinating, isn't it? There is a lot more in this video, linked below. Feel free to discuss this and other examples you found on the forum.
Another example here, mosaicing. Now, we've talked about mosaicing before. We talked about panoramas, about aligning images and bringing them together. Well, instead of just a small, discrete set of images, suppose you actually have a video, so you're taking your camera and you're panning it around. What you might want to do is make a single image, okay? And this comes from Michal Arani's work, of where you can see where all the frames are. Okay, you can sort of see this jagged line, each one being the edge of a frame, and you realize what happened is the camera was swept out this way, all right, and I'm able to make this single image, all right. And if I'm rotating my camera about its axis, I'm not actually doing any translating, the reconstruction can be perfect because I don't have any motion parallax. And if these things are planes, I have to align some points. How many points does it take? It's a homography question. That's right. Even Megan got 4 points for that. And in fact, if I am moving but things are really on a plane, it's still 4 points. So there are other applications of motion analysis, segmenting objects in space-time. Sometimes you can get the three-dimensional structure. If you know how the points are moving, you know which point is which, just like when you saw the person. You might want to learn the dynamics of how something's moved. Maybe you're doing physiology, and you're watching people moving, and you want to understand something about their gait and the dynamics of their gait. All right? Recognizing events and activities. You'd like to be able to say, what just happened in the video? So it's not just object recognition, it's action recognition. And finally, you might just want to process the video and understand the motion to improve the quality. So you might do motion stabilization, right, so that you've got this jerky camera and you'd like to get a nice smooth video out. There are simple ways of doing that and complicated ways. In fact, a colleague of mine here, Irfan Issa, and a former student of mine, Vera Quatra, and some others did some work on stabilizing video, especially when you have rolling shutters and cell phones. Anyway, these are all reasons for wanting to process motion. So for the remainder of this lesson, and then the next one, and then the next one, and the next one too, we're going to be talking about motion estimation. Basically, given a sequence, tell me what moved, tell me how it moved. Generally, you can say there are two different approaches to this. The first approach involves feature-based methods. Now, feature-based methods are just what you might think. Extract some visual features like corners, textured areas. Oh yeah, we know all about that. And track them across multiple frames. So that is, find them from one frame into another. Oh, we know all about that too. And that will give you what's called a sparse motion field. That is, you don't have the motion of all the points. You have a motion of a bunch of points that were good to track. All right? But that works really well when image motion is large, so you move like tens of pixels, and you have a significant change between frames. The other method, class of methods, are what are called direct or dense methods. In dense methods, you're sort of directly recovering the motion of every pixel, of each pixel, from the fancy word is spatial temporal image brightness variation. So in other words, remember that volume, x, y, and t? So you can think of gradients, you can think of flow within that volume. And what you're trying to do is you're trying to recover that flow based upon how the appearance changes over time. It gives you a very dense motion field, but it can be sensitive to appearance changes. This type of analysis is suitable for video, where you're getting samples very quickly, so things don't move very much in time. And in fact, if things are somewhat smooth in time and space, I could say, well, from one frame to a next, I can talk about how things are moving, like, say, a first derivative. If you're worried that a Taylor series expansion is in our future today, well, maybe tomorrow, yes. Okay, but the idea is that it's good for nice, dense, smoothly moving things. We've already talked a lot about finding features, detecting them, describing them, and matching them. And so we're not going to do much more in terms of that feature matching for motion. Okay? Instead, what we're going to be doing over the next couple of times is focusing on the dense methods, where we look at the derivatives, we look at how things change. And just to sort of spill the beans all the way at the end, the best methods currently use a combination of the feature to get the long-range matches and local gradients in order to get the dense, shorter range. So you already know about the feature stuff, so now we need to go over the dense, direct stuff. And that's what we're going to be doing over the next couple of lessons. Welcome back to the Georgia Tech Metropolitan Opera, where we will be singing about computer vision for the rest of the day, because I am like going nuts already recording all these lectures and I have to do something differently. However, as my children will tell you, my singing about anything is generally a bad idea. So let's chat instead. So last time we were talking about motion. This is within this general context, and we talked about that if you're looking locally, you can't actually tell the direction of motion of a pixel. And that was referred to as this aperture problem. Remember this little demo where we said that even though the actual thing is moving sideways and down a little bit, you see it as moving upwards, because the only part that you can see, that edge, all you can tell is the direction of motion in the direction of the gradient. And we showed that here, that that was derived from our brightness constraint equations, where we showed that the UV dotted with the gradient has to be the negative of IT. That's what that equation says. But any UV, any motion whose component perpendicular to the edge along the gradient is the same would be an acceptable UV. So we needed some additional constraints. So last time we talked about introducing some global requirement. We talked about a smoothness constraint that would allow us to optimize a solution over the entire image. But today we're going to look at more local and frankly much more effective, or certainly more commonly used methods. So how are we going to solve the aperture problem? Well, look, the basic idea is the same as before. We have to impose some sort of constraints, but this time we're going to impose some local constraints to get more equations per pixel. So for example, we talked about maybe we'll assume that locally, right around this point, the motion field is very smooth. In fact, how smooth do we want to assume? How about we assume that it's actually the same value? That is, over a window, we're going to assume that UV is the same value everywhere. So if we were using, let's say, a 5 by 5 window, so there's 25 pixels, if we were assuming that there was one UV for all of these, the UV for, let's say, the center pixel, that would give us 25 equations per pixel. And here they are. So what we've got here is, here's our U and V that we're assuming is the UV of some center pixel. And here we have 25 rows of the derivative of x and the derivative of y at each of those 25 points. And these are the gradients dotted with UV equals the negative, and here is the temporal derivatives at each of those points. So I can write that as AD equals B, where D is this displacement vector UV, and B is just this 25 by 1 vector that is essentially the negative of all the temporal derivatives. Okay? So we have this equation, AD equals B, and it's got 25 equations and 2 unknowns. All right, well, so that's a little bit of a problem. How do we solve a system when we have more equations than unknowns? Well, we do our standard least squares solution. When we have an equation like this, we say, well, we're going to minimize the square difference, okay? And the way you do that is by using the standard pseudo inverse method. So we multiply A by A transpose, and since A is 25 by 2, A transpose is 2 by 25, so A transpose A is just a 2 by 2, and D is a 2 by 1, and A transpose B is a 2 by 1, and we end up with this equation right here, okay? And these have the terms written out, and these sums are summed over whatever the window is that you're summing over. So it's 5 by 5 would be over all those 25 pixels. And over here you just have the product of the sum of the product of the image gradient times the temporal gradient. This is what we have to solve. And by the way, this technique was first proposed by Lucas and Canati way back in the dark ages of computer vision, 1981, which is not quite the dark age, it was the dawning of it. The dark ages were in the 60s. All right. We just did that. We can solve our least squares and come up with a solution. But let's understand exactly what solving this means, okay? So you remember the aperture problem, right? And so here it's drawn out that the idea is if I have a gradient in some direction, and so this is my little gradient there, all right? So that any UV that's along this line would be an acceptable UV. That is, any UV whose component in the direction of the gradient would be acceptable. And that's what this says, that there's a single equation for that. And that's the equation of a line in UV space. Thinking about UV space, if we have a particular gradient, that gives us a line. That's what this red one shows us. But suppose we have another gradient, okay, but in the same little window. Well, that gradient would give us a different line. So this is gradient 1, this is gradient 2. Over within the same window, and then here's gradient 3, and it gives us a different line. Clearly what's going on is if I have a bunch of these different gradients, they're all going to intersect at the point. That point is the correct UV. So as long as we have different gradients within the window, we can get a solution. We've seen this before, haven't we? Here is the equation we just showed you, A transpose A times E equals negative A transpose B. All right? When can that be solved? To just solve this, we would want A transpose A to be invertible, right? Because if it's invertible, I just multiply both sides by that, and I come up with a solution for D, okay? Well, when are matrices invertible? Well, from our linear algebra, we know that they need to be what's called well-conditioned. If they're not well-conditioned, then the inverse is unstable. And basically, you can look at the eigenvalues, all right? And the ratio of the largest eigenvalue to the smallest eigenvalue shouldn't be too big. That's from your conditioning. In fact, if the second eigenvalue were 0, lambda 1 over lambda 2 would be infinity, and that'd be awful. All right? So what we want are eigenvalues that are, approximately the same magnitude. Okay, so that will make it solvable. But wait. We also know when this should be solvable from the geometric demonstration we just did. This whole problem should be solvable as long as there are different gradients within the window. Because if there are different gradients within the window, then we get those intersections of those lines in UV space. So does this remind you of something, gradients and eigenvalues? Of course it does, because you're like right on the ball, all right? You remember our Harris corner detector? This matrix, A transpose A, that is the second moment matrix of the Harris detector. And if you remember, we looked at the eigenvectors and eigenvalues of that matrix to know whether or not something was a good corner.
Memory check. If lambda 1 and lambda 2 are the two eigenvalues of gradients in a region, when do you think that region is good for tracking motion? That is, when do the optical flow equations become solvable? Is it when lambda 1 and lambda 2 are small? Or when lambda 1 is much greater than lambda 2? How about the opposite? That is, lambda 2 is much greater than lambda 1, say an order of a magnitude larger. How about when they're of comparable magnitude and sufficiently large? Remember, select the cases where the optical flow equations become solvable. That is, you get definitive values for u and v. We've seen this before during Harris corner detection. The answer is when lambda 1 and lambda 2 are both fairly large and of a comparable magnitude, it means that there are multiple gradients in the same region that can be used to locate the gradient direction correctly.
right? Remember this picture here where we take a look and we say, well, if both of our eigenvalues are small, then this is a flat region, there's not much. If only one of the eigenvalues is big, then that's not good. And here lambda 1, lambda 2 is in the order. If we make them lambda 1 always being the biggest one, then of course lambda 2 is bigger than lambda 1. But the idea was that we were only in a corner if both lambda 1 and lambda 2 were kind of large. All right? And remember, we said that we didn't have any decent corners here in the blank area that was in the sky. Well, guess what? You can't really tell the motion either. All right? Likewise, we said it wasn't a good corner if you were along an edge, because the corner could slide along that edge and we wouldn't know where it is. Well, movement happened along the direction of the edge and we wouldn't know how it moved. So where can we estimate motion really well? Well, we can estimate it really well in this textured region. Basically, the same constraint that we had on the Harris corners, namely I have to have the gradients varying over the window, and that's indicated by having two reasonably large eigenvalues of that second moment matrix. That's the same thing that applies to motion estimation. One quick note, if instead of doing this in black and white, you were actually doing this in red, green, blue in a colored version, right? You would now have, instead of 25 equations, you'd have how many? You'd have 75 equations, 5 times 5 times 3. Now, if you're really shrewd, you might say, wait a minute, wait. Suppose my window was only a single pixel. You told me, Professor Bobak, that we had this problem, okay? That we had one equation and two unknowns. But with RG and B, I now have 3 equations and 2 unknowns. Can't I solve it? Well, no, Frodo, you cannot. All right? The problem is that the RG and B images, so you can just think of the image planes, are quite correlated. Okay? So, you know, you have a change of intensity, but you have the same changes of intensity because of the edge of my shirt, both in the green and in the blue channels. Now, one might get brighter and one might get darker, but the gradients will be in the same direction. So the gradients are very correlated, so you can't just use the different color planes in order to solve it. Good try, though, sort of. So what I just showed you is the basic Lucas-Canati method, kind of elegant. Basically, we've made a lot of assumptions, and these assumptions can give us errors. The biggest error we have, that is the assumption that we made that's in some sense the most wrong, is the idea that the motion is small, okay? Often, motion is large. And when motion is large, a couple of things are wrong with the Taylor expansion. One is, even if things are nice and smooth, they may not be linear. So we were doing a first-order Taylor expansion, not a second order, no second derivatives here. So that assumes that things are planar. Well, suppose things are curved a little bit. Well, we're going to handle that, in fact, we're going to talk about that in a minute, by doing something called iterative refinement, which is we're going to assume it's a plane, solve it, move the picture over a little bit, do it again, until we've converged finally to the right point. And it allows us to handle the non-planar component. But in some sense, even even worse than that is maybe I've got a nice bright pixel here, and then the bright pixel jumps over a bunch of dark pixels. So it's not even, and then there's some other, so it's not even local anymore. That is, I can't find where I went by just sort of following my derivatives. And the way we're going to handle that is with a course-defined method, which actually we're going to do next lesson. Today, this lesson, the only remainder thing we're going to talk about is this iterative refinement. So iterative refinement is designed to handle the fact that things are not exactly tangent. And so here's how it works. I'll write down the algorithm, and then it's a lot easier to see in a picture. All right? So the first thing is, the way you do it is, you say, okay, I'm going to pretend, I'm good at pretending, that it's just going to work. All right? So I solve for my velocities using the standard Lucas-Canati. So I assume linear Taylor approximation, I solve for UV. Great. So now I've got a UV at every pixel. Now it says I'm going to warp IT to IT plus 1, okay? We talked about doing image warping when we were applying transformations. And those of you who are going to do the OMS problem set, you'll probably get to know and love how to do warping. But basically, The UV says how to move every pixel from one image to get to the next one. So you know what? I take this picture and I move all the pixels. And if you remember, we have to do this backward warp so we don't end up with holes. If you don't remember that, go back to the transformation lecture where we talked about warping. But the idea is that we essentially distort the T image to move to where I think all the pixels go. So it's almost the T plus 1 image. But it's not exactly the T plus 1 image, is it? It's close. So what do? I just do it again. I take the image that I created and I compare that to the real T plus 1 image. And I get a small amount of more motion. I could actually add that motion to the original motion. That's the new flow field. Well, I can take that one that I created, move it a little bit, and what do? Do it again until the pixels stop moving. And that will converge to a solution. So that's really easier seen here graphically. So here I have two curves, okay, F1 and F2, and those are meant to be as taken in two different times. And here I'm just looking at this point x0, and just so you understand, this is the value at, if you will, time 2. This is the value at time 1, and that's true for all of these. And the question is, how much does the curve move? So what I have to do is I want to find this displacement at x0. All right? So do it as follows. So here's how we do. We initialize, since this is iterative, we have to initialize. We'll first start by assuming that our displacement was 0. That is, u and v are all zeros everywhere. That's great. That makes the warp really, really fast. I don't do anything. It's the original picture. Now I have to estimate the next one, d1, by figuring out what the new displacement is. That's what this new little delta d is going to be. So how do I do that? Well, I have to compute these tangents, and you can see the tangents are right there, okay? And what I do is, based upon that tangent, come down here, it says, oh, okay, if this thing were actually a plane, this amount, that's my d hat. That's the amount I have to displace over in order to line up these points. That's assuming this thing were a plane. And if it really were a plane, that would be the amount that I would have to move. So let me do that displacement, and I end up there. So now I've got my d1, which was just d0 plus my new estimate. And guess what? I have to do it again. So now I take a look and say, I have to move this amount. So I add that to my d, and I move it that much. And guess what? I do it again. Estimate tiny little d hat this time, and voila, it turns out that f1 of x minus d3 is almost exactly f2 at this point. Okay? That's the iterative refinement. And the only thing that it takes in order to do this iterative Lucas-Canati beyond the regular one is this warping step. Given some UV that you've computed between one image and the next, take that first image, warp it through that flow field, and now you'll have almost the second image, and you just apply it over again. A couple implementation issues. In general, warping is one of those things that in principle should be really easy. In practice, you always make mistakes. I will say that MATLAB does a very fine job of allowing you to do warping in particular ways. So if you're using MATLAB or Octave, it's easy. And I think within Python, NumPy, OpenCV accomplish it as well. The other thing in order to make this work, and actually we'll get to this when we do the whole multi-scale, is it's often useful to sort of take a nice bit of a low-pass filter of your images, smooth things out. Why do you want to do that? To get sort of your smoother derivatives as things work. And we'll talk more about that next time. That ends the basic discussion about Lucas-Canati. It was actually done for stereo reasons, which is kind of funny, because in stereo, you know that points have to move along the epipolar line. Whereas in motion, they can move however they happen to move. But it was originally derived in a stereo formulation. It's actually used a lot more now in the whole process of doing motion. To actually make Lucas-Canati work, you're going to have to do things hierarchically. That is, you're going to do things at a coarse scale and then get to a finer scale and a finer scale. And it's a really good example of doing multi-scale processing on images, and that's actually why we're going to do it next time. All right. Welcome back to Computer Vision. Last time we introduced the notion of image motion. We said how motion is actually a construct of your head because there's just a bunch of static frames, and your mind, your brain induces this notion of believing that there's actual motion. So the question then becomes, how do we compute that motion? And we talked about motion estimation techniques are going to be the methods of doing this. The first one that we mentioned was feature-based methods, where you detect, describe, and locate features in your subsequent frames. And we've done a bunch of that in looking at how we do the SIFT stuff and panoramas and those kinds of things. But the other methods were called direct or dense methods. And that's what we're going to be focusing on today. Direct and dense methods, what they do is they recover motion at every pixel in the image, and that gives you a dense flow field, and it's based upon what we call the spatial temporal brightness variations, how the appearance is moving and it's changing. It can be sensitive to appearance changes, but as long as you're getting sort of video-like sequences where you have frames sampled regularly and frequently, it works pretty well. The first thing we have to do is define what's called optical flow or optic flow, because what we're going to be recovering today is the optic flow. And the optic flow is the apparent motion of objects or surfaces or pixels. And the reason I say apparent will be clear. Here what we have is a Rubik's Cube looking device, although here it's black and white, so it's just a denuded Rubik's Cube. And it's been placed on a turntable that's been rotating around this way. If you take a look at these little patterns on the side, you can see what the rotation is. I'm pretty sure this was done by Rick Zaleski because he looked at these gray codes to do the rotation. Now, what's a little bit hard to see is that over here are these little arrows that are showing you the motion. And of course, the motion is greater in the front of the turntable than, say, on the cube because it's closer to you and it's rotating a further distance. But you'll notice that there are no arrows up here, right, on the white part of the turntable. Now, it's moving exactly the same way as the part of the turntable that has the markings on it, but you can't see it. There's no apparent motion because there's no contrast, there's no texture, there's no indication that the pattern is moving. So optic flow is recovering the apparent motion of objects or points or surfaces. The actual motion, by the way, is sometimes called the motion field. We're not going to talk about that today. We'll talk about that, not next time, but time after a little bit, but what the underlying physical motion is. Today we're talking about motion in the image. So let's take a look at a sort of very simple definition of the problem of optical flow or optic flow. So here I have 4 points, conveniently color-coded so you can tell their difference. And this is their location, x, y, at some time t. But they're all going to move, okay? So they're all going to move in some direction such that at t plus 1, they're at a different location. And that's drawn here. So the points moved in the direction of the arrow. You don't actually get to see them doing the movement between t and t plus 1 because we only get samples at t and t plus 1, but that's just showing you how they move. And in some sense, our goal is to actually recover those arrows. So the question we want to ask is, how do we estimate pixel motion from image I xy of t to image I of xy t plus 1? We're trying to estimate that motion. So what we have to do in order to estimate this pixel motion is essentially solve a different kind of correspondence problem than we had from stereo. It's kind of sort of related, but somewhat different here because the pixels can move however they want. Given some pixel in I, x, y, t, so here's one, here's one, here's one, here's one, look for nearby pixels of the same color in x, y, t plus 1. Solving this problem is what's referred to as the optic flow problem or optical flow problem. And in particular, we're going to have to look at 2 words. One is this notion of nearby, and we have to look at what we mean by the same color. What we want to do is we want to look at these terms, nearby and same color, a little more carefully. So we have 2 key assumptions, this notion of the same color and nearby. The same color is referred to here as color constancy. And basically this says that a point at xyt, if we knew how it moved to some point x prime y prime at t plus 1, that point will be the same color. Okay? So, and if this is a monochrome image, grayscale image, then that point will be the same brightness. Okay? And that's the color constancy or brightness constancy. All right? And then the second thing is that we're going to assume that these points don't move very far from one time to the next time, from t to t plus 1. And if you think that's because we're going to do something in the Taylor universe, you're absolutely right. So let's look at these equations a little more carefully. So the brightness constancy equation. What we're going to do is assume we know that some pixel is moving an amount uv. U is the amount in x, v is the amount of y, when we get to t plus 1. Okay? The brightness constant constraint equation can be written like this. I of xyt, that is the image at time t at location xy, brightness if it's grayscale, color if it's color, is going to be the same at t plus 1 at location x plus u, y plus v, where u and v are the amount the point has moved in the x direction and the y direction respectively. So that's called the brightness constancy constraint, and in fact I can rewrite it like this. 0 is equal to the x plus u, y plus v, t plus 1 image minus the original I of xyt. All right, that's the brightness constancy constraint. The second assumption was that we get a very small amount of motion. Okay, so that basically u and v, let's assume they're like 1 pixel or part of a pixel, or just things are changing smoothly. Yes, you know what's coming. What that means is I can estimate, using the Taylor expansion here, that the value of an image displaced from x by u and displaced from y by v is approximately, well, it's exactly here by order terms, it's the original value plus the gradient x times delta x plus the gradient y times delta y, u and v are delta x and delta y respectively, plus some high order terms. Right? Remember Taylor expansion, if you go infinite series, you get the exact solution, but we're just going to say plus some high order terms, and then when we make those high order terms go away, poof, wow, isn't that great? I've got the power right here. All right? Then we say that it's an approximation, okay? So we say that x plus u, y plus v is approximately the original image plus the gradient in x times delta x plus the gradient in y times delta y, or v. Okay, so now I've got these two equations, I can combine them. The first one is obvious. This is the original brightness constancy equation. The second one, after I substitute in the Taylor series expansion, there's a little sleight of hand going on. What I'm doing is I'm substituting for this value. Remember it says that I can get the location at x plus u, y plus v. All right? I can do the Taylor expansion. So here's the original xy at t plus 1. And then there is this derivative part, okay? I of x times u, I sub y times v. And I of x is the derivative in the x direction. I of v is the derivative in the y direction. Now, students will usually ask me, wait a minute, is that a time t or a t plus 1?
Is that a time t or a t plus 1?
The short answer, doesn't matter. The idea is we're going to assume that things are changing so slowly and so gently that the derivative at a particular point is going to be the same whether I look at t or t plus 1. It's a little bit, shall we say, dicey, but actually in the limit it's true, and we only care in some sense about the limit. So taking those two equations, I've now rearranged things. I just moved this part over to here, and then in the next line what I did was, this is I sub t. I sub t is this difference there between I of xy at t plus 1 minus I of xy at t. Well, what is I sub t? Well, if I of x is the derivative of I in the x direction, and I sub y is the derivative of I in the y direction, I sub t is the derivative of I in the time direction. It's what's called the temporal derivative. And remember, our imagery is now a function of x, y, and t. So I can take a derivative in x, in y, or in t. Another way to think about it is, if I just look at some point x, y, and I see how much the image changes from t to t plus 1, that's my temporal derivative. And then finally, on this last one, you'll see that this here is just ix times u plus iy times v. That's just the gradient, ix, iy, dotted with however the point is moving. That's uv. So we write that like this, that 0 is approximately it plus the gradient of the image dotted with this vector uv. uv is the direction of motion. Got it? Cool. All right, keep going. Now, this is approximation in the limit as u and v approach 0. Now, you might ask, how can u and v approach 0? Well, the idea is that in the limit, of course, if t was very small, the amount of motion you'd get would be very small. You would just have the direction. So we're going to assume that they're very small, and we're just going to take this equation directly as is, that 0 is equal to it plus this gradient, and that, written out either above as a gradient or here in algebraic form, that's the brightness constancy constraint equation. Say that 5 times fast. Brightness constancy constraint equation. All right, IXU plus IYV plus IT equals 0. So here I have the equation written, and I've written it both ways, just the original, the way using the gradient imagery dot product way, or in the algebraic way. Question: how many unknowns and how many equations per pixel? The number of unknowns is easy. What was I trying to solve for? U and V, right? U and V is which way is this point moving? Great. How many equations? Well, yes, there are 2 equations up there, but they're the same equation. I have 2 unknowns, but only 1 equation per pixel. This should bother you, right? It's very hard to solve things that you've got twice as many unknowns as you have equations. Because remember, I have a different U and V possibly for every pixel. So I've got 2 times the number of pixels unknowns, and I've got 1 equation per pixel, 2 times the number of pixels. What's going on here? So intuitively, we can think about what this constraint means as follows. The component of UV that's in the direction of the gradient, that's what we can measure, right? That amount will tell us how much the image will change. That's why that's the amount of IT, I sub t, the derivative, right? So what this is saying is if this is the direction of our gradient, as indicated here, right? Here, suppose this is my real UV right there. Well, any other UV that has a component of the same amount in the direction, but I've got a U prime V prime, that's in an extra component that's parallel to the edge, all right? And this new vector here, which was the original U V plus U prime V prime, it has the same amount perpendicular to the edge in the direction of the gradient, but a different amount along the edge. Remember when we were doing corner finding and we put up a thing and we said, well, if you slide it up and down, if your little patch is on the edge of the black square, if we slide it up and down, we can't tell at all. We can only tell how much is being moved perpendicular to the edge. That's what's going on here. Locally, we can only tell the amount of motion that is perpendicular to the edge in a little area. When you think about this little area, you can think of it like looking through a little hole. Remember from our talk about cameras that's called an aperture? And this general problem, this is called the aperture problem. So here is a very interesting line drawing. It's a line with 2 parts. And notice it has a corner. And here's the next one. Voila, it moved. Back, forth, back, forth. I can do this all day. Okay? And you can see it moving. Okay? Great. Let me put an aperture over that. So here is a great big green aperture. All right? And now I'm going to move that line thing the same way. And now it goes like this. Whoa. Now it's moving up. Or at least it feels like it's moving up. Is it moving up? No. In fact, here I've made it transparent. Okay? So now this is the same motion, right? If you look at the corner, you can tell this thing is moving over and down a little bit. But if you were to look just inside the circle, it looks like it's moving up, not down and over. That's the aperture problem. Okay? You can only tell the motion locally in the direction perpendicular to the edge. There are some other effects of getting sort of strong gradient flow. So this is a single pattern. And then I'm going to use PowerPoint to just put this in motion using animation. So there's no video going on here. This thing is just moving back and forth. And hopefully, as you see this move, every time it bumps, you're going to see the inside move relative to the surround. It's not actually moving. That's in your head. And that's because of various noise and various ways of computing the gradient. More details, and it's not just the aperture problem, but it's showing the sensitivity in your mind, in your head, of the gradient. The aperture problem also is sometimes used to explain the barber pole illusion, right? So it's spinning around, but you see stripes going up. And in fact, in the you shouldn't believe everything you see on the web universe, some people will say that the aperture problem explains the barber pole illusion. But actually, that's not really true. It has to do with it. It doesn't explain it. Because if you think about it, the gradients here are not quite vertical, right? They are off a little bit. And so you can get a flow that's like that. And you have to do some integration to decide that the whole thing is moving up. And actually, Ellen Hildreth, a very long time ago, in her PhD thesis, looked at how you use the normal flow and you can integrate it in order to make you might see the pole move up. But it is the case that there are places out there that will tell you that this is because of the vectors.
Let's say we have a bright edge that we can see at time t. The same edge at time t plus 1 has clearly moved to the right. Now when analyzing the optical flow here, you might think, what aperture? Is there a magical green donut that is forcing you to look at small parts of the image at a time? Well, no. It's because with the brightness constancy equation, we're trying to analyze each pixel at a time. We look at the image intensity at that specific location xy, how that changes from time t to t plus 1, the horizontal and vertical image gradients, again at that specific location, and we try to compute the displacement uv for that particular pixel. Since there is no actual aperture limiting your view, how would you improve this approach to get the correct optical flow? Think about what additional constraints you might be able to use. For instance, do you think nearby pixels move together, that is in the same direction and roughly the same amount? And can this be used to optimize our optical flow computation? Similarly, can we say that motion over an entire image should be consistent? Or should we just look at distinct regions, like corners? Select the choices that you think are valid and useful. Anything else? Mark Other and enter it in the box. Yes, nearby pixels tend to move together. This is because an object seen moving in a certain way occupies more than a few pixels. Well, otherwise it would be hard to see. This can be thought of as a local constraint, and we'll see more of this later. Saying that motion must be consistent over an entire image is a pretty bold claim. But it is still fairly valid and useful, especially when used as a soft constraint. This means you're not saying that motion across the image has to be identical. It's just that solutions to the optical flow problem that generate consistent motion are preferable. As you might have guessed, this is a global constraint. Remember that our goal is to compute optical flow at each pixel, that is, dense flow. Now if we consider only distinct regions, then how are we going to do that? Well, at distinct regions like corners, the ambiguity of flow direction is small. If we compute optical flow at these regions, we could interpolate the flow between them. So yes, this is a useful approach as well, although it might result in approximate flow. Anything else you have in mind? Don't agree with these constraints? You know where to discuss.
All right, so we have a problem. The brightness constraint equation gives us more unknowns than equations, more directions to move than we have pixels. How are we going to recover the motion? Obviously, we need some extra constraints. We need some additional constraints. So we'll talk about sort of a global approach now, and the next time we'll talk about a more local approach that actually is used, and in fact, some of you may even implement. Sometime long, long ago in a galaxy nearby, Bertolt Horn and Bernhard Schunk did some work on what was called smooth optical flows. And basically they said, let's try to come up with an optical flow that minimizes some error. Okay? So the first part of the error is how much do we violate the brightness constancy constraint equation, right? Basically, that middle term right there, that's supposed to be 0, right? IXU plus IYV plus I sub t is equal to 0. So violations of that mean that it's not 0. Sometimes it's positive, sometimes negative. I square it and I sum it up over the whole image. That would be how bad my flow is with respect to the constraint equation. All right? But we know we can solve that exactly because we have more unknowns than constraints. So if that's our only constraint, we're not done. But we're going to call this the constraint error. By the way, I kept partially, originally I had stolen, then I did it on my own. I kept the integral signs instead of summations because back when this work was done, we'd like to think about images as actually continual functions. Of course, if you were to implement this, you'd actually have to do summations. I will also tell you the fact that summations are not integrals matters. And if you take a look at some of the work that was done in shape from shading, doing it as an integral was actually hard. Doing it as summations was in some sense a little bit easier. But for here, the difference doesn't matter, so I just wrote it as being summed up over the image. So here we have our optic flow constraint term. Now we need another term. Well, it says smooth optical flow. Here's the idea. Remember when we did stereo, the state-of-the-art solution that I showed you that did that beautiful recovery, used a bunch of terms, some that had to do with the data, but it also had to do with the smoothness of the disparity field. That was the idea that surfaces don't change a lot all over the place, but they tend to have a particular depth or vary smoothly. The same could be said of motion. That is, so if I've got something moving around, the motion vectors from one point to the next change slowly. So let me come up with a penalty term that says I really don't like velocity fields where the velocity changes quickly from one location to the neighboring location. So that's shown here. These ux, uy, that's the derivative of u. Remember, u is the x component of the motion field. The derivative in the x direction squared, because it would be positive negative. Derivative in the y direction squared. Same thing as here, which is v sub x, v sub y, the change of v as you move in x, the change in v as you move in y. Again, everything is squared. So the idea is we would like this thing to be like 0 or as little as possible. By the way, what would it mean for this to be 0? Well, for this to be 0, that would mean that all the u's were constant, right? They were all the same value, so the derivatives would be 0. And all the v's would be constant. So if all my pixels were moving with the same UV, the whole image was moving the same direction, this value would be 0. Any other u's and v's will cause this term to have some value, and we want to try to minimize this thing. So now we have these two terms. We have the constraint equation error term, and we have the smoothness error term called E sub c, E sub s. And what we want to do is we want to find the UV at every pixel, and there's going to be a different UV at every pixel, that minimizes this total error, which is just the smoothness term plus some weighting factor times the constraint term. And the weighting factor is sort of how much you believe your data. So the bigger the weighting factor is, the more important the satisfying the brightness constancy constraint is. The smaller the weighting factor, the more the smoothness term dominates. And what value it should have is a function of sort of how much noise there is and how smooth you believe the entire thing is. So this was part of a general approach, variational approach, where you're going to solve for UV as a function of XY. That is, you're going to find the optic flow, U and V, for every pixel that tries to minimize this error. It's somewhat painful to try to implement systems that can solve for that. Not impossible. But the idea is that you have a global constraint, the smoothness constraint, to help solve your problem. So that's one way. You impose a constraint on the flow field in general. It has some strengths. Like one of the strengths are that it allows you to bias your solution with a particular prior. That is, like you really prefer smooth, or maybe you prefer more translated. The idea is you work some constraint into a general overall thing. I will tell you that in general there are much better ways of doing it than this, in particular imposing constraints on a local basis, and guess what? That's what we'll do next time. Welcome back to Computer Vision. With today's lesson and the next, we're going to close a circle that we started, it seems like forever ago. Remember we were talking about trying to compute transformations between images, and we talked about doing panoramas and mosaics and other ways of doing this. And we said, and also when we were talking about fundamental matrices, key to all of these things was if we knew the correspondences, you could compute the various transforms, whether it's homographies or something else. Then we talked about computing features, and feature points detections and descriptions. So today we'll finish the story where we're going to actually do the approach for doing feature-based alignment. We'll describe it as a form of model fitting, since really that's what you're doing. We'll show you more about that. And then we'll talk about a really cool method that lets you effectively find the best global solution, or probabilistically the best global solution, without being too exhaustive, too combinatorically challenging. All right, so let's remind ourselves of the overall strategy for doing feature-based alignment to find transforms. We know how to compute features. That involves both detection, remember all that Harris-Laplace stuff, for finding feature points, and for generating descriptors. We talked about SIFT, where we generate descriptions around the little local neighborhoods of the points. Second, we know how to find some plausible, or what we're soon going to call putative matches. We talked about doing the variation on KD trees, the best bin, hashing methods, basically ways of saying, well, which features are likely to match which other features. I might make some mistakes, but at least they get me some reasonable matches. Then we would have to compute a transform that aligns one image to the next. We talked about doing homographies or affine transforms, and then finally you would apply that transform. Great. All right, so the algorithm follows this pretty carefully, but you'll see in a minute we're going to get to a point where there's a step that we don't know actually how to do. So the first is extract the features. Fine, we do that. Second is compute these putative matches. That's the term that's used. This is what I was talking about doing this KD tree or the best bin. And what you see drawn here, all those red arrows, those are going from some feature in the left to the best feature matching it on the right. Now, if this was nice, if everything was right, you'd see this nice smooth transition. But of course, what you see here is a lot of stuff. In fact, you can see, some of these things tend to be all lined up the same direction, but here's one, right? It goes from here to there. That is clearly, I think the technical word is wrong. So what we'd like to do is somehow figure out a solution to this that makes it clear that we're going to ignore that one and pay attention to another. So after we find the putative matches, then we have the loop until happy routine. Okay, so loop until happy says, hypothesize some transform T from some of the matches. Actually, this is what's going to be interesting, the sum of the matches, okay? And then we're going to verify the transform. We'll talk about what that means in a minute. And we keep doing this until we think we found a solution that's really good. That's what it means to loop until happy, at least today. And then you apply the transform. So how to get the putative matches? We've talked a little bit so far about essentially doing exhaustive search, where you compare one against every other and you pick the one that's best. We also talked about hashing and nearest neighbor techniques. But you now find a best match. How do we know it's a good one? Okay, so in this next lesson, not today, we're going to talk about looking at the global solution that's suggested by this match and using that to prune off some of these. But even before that, there's something we can do at the local level. And here's the idea. So we're not going to match everything. We're only going to match the ones that have good enough matching. All right? So how do we do that? Okay? Well, here would be a simple idea. You find the best match, and you take the correlation, a little patch from here, a little patch from there, and you do, it says here SSD, sum of squared differences. Remember we talked about that? And we could say, all right, well, if that number is less than a certain threshold, we're going to accept that match. By the way, something that I've said before and is implicit here, and we'll say it again later, the general idea is I need to find enough good matches, not all of them, and I need to not find too many bad matches. So the goal is to try to get a bucket of good matches with only some bad matches thrown in. So going back to the SSD, the question would be how to set the threshold. So empirically, you can start to take a look at this, all right? So let's suppose you have a whole bunch of matches, and since you, the human, are going to click on which ones are correct and which ones are not, well, actually, not you. This is what you're going to do if you're a professor. You're going to find a bunch of undergraduates, okay? And you're going to offer to pay them not very much money, and then you're going to offer to give them pizza, okay? You can get undergraduates to do anything for pizza. Turns out you can get graduate students to do anything for pizza and Coca-Cola. So anyway, so you get an army of students to click on which matches were correct and which matches are not correct. So after everybody's clicked on all these matches, you can actually generate two graphs. What you're going to do is you're going to measure the nearest neighbor squared error. So this is how good is the SSD of the nearest neighbor. And we're going to check it for all of the correct matches and all of the incorrect matches. So incorrect matches, remember, are where the best match is actually not the right one. Okay, so we're just plotting the best matches, but the correct, the ones that are correct and the ones that are incorrect. And so here is the squared error of the correct matches. That's what it says here, correct matches, all right? And you'll see that it falls off nicely. So most of them tend to be small, and, you know, a modest amount of them tend to be large. So you might say, well, I'll just set a threshold here and that'll be fine. Well, except not so fast. If you then take a plot of the incorrect matches, you see that the incorrect matches have a whole bunch of stuff early on also. So what that means is I've taken a point and I've found its best match, and the best one is not the right one. So it's not a surprise that it's a lowish value because this is the best match. The problem is that some of your best matches are correct and have a lowish score, but some of your best matches are not correct and they also have a low score. So it's not so clear where you should set that threshold. So in David Lowe's work and doing the SIFT work, he had a pretty clever idea, and this is the idea. Take your first nearest neighbor. So you do the best match. See what its score is. Now, we already said setting a threshold just on that is challenging. But here's what he's going to do. Take a look at the next best match. So I now have the first nearest neighbor and what's called the second nearest neighbor. And take a look at the ratio of the best to the second best. Now, if you think about this, before we get to the plot, when you're a correct match, the best is really good and it's the best one. And the next best one, well, you know, presumably it won't be, we know it's not going to be as good, and however much it falls off will depend upon sort of where in the image there happens to be another point that just happens to look like this one. So you're going to get that ratio, all right? But now consider a point that is not the right one. So it's sort of randomly, maybe its real match was occluded. It's not actually in the picture. So it randomly went and picked some point that happened to be its best match. Its second best match is going to be some other random point in the picture. So those are going to be more similar in value than in the correct case. And that's exactly what this graph shows. This is the ratio of the best to the next best, okay? And what you're seeing here is for the correct matches, the distribution is over here, okay? So that ratio of error, okay, is, you know, a lot of the stuff is over here, right? So like this 0.1 would mean that the best match SSD, sum of square differences, right, which you want to be low, is 10% of the next best match. So that's really a big difference. Here it's 20%, 30%. For the incorrect matches, remember, it's randomly selecting them. You hardly get any that have such an extreme ratio. And in fact, you don't start seeing them show up until you get to this much higher value. So setting a threshold here, you could set a threshold, you know, right about there. And almost all of your matches, your best matches, would have been correct ones. And very few of them would have been incorrect. Now, you might ask, but wait a minute. You're going to throw out some correct matches that way. Isn't that a problem? There's no way Megan's going to be able to remember that entire question. So you might just say, well, aren't you going to throw out these here that are the correct matches, but their ratio didn't pass your test? Yep. So you're going to be throwing away some correct matches. But our assumption is that we've got plenty of correct matches, and we just have to figure out which ones are there. Okay, so that's this cool method of doing this selection by comparing the best to the nearest best. Cool? Good. So now we have some more, another trick under our belt that allows us to do this feature matching, whether we're doing the, or really in this case, throwing some features away match selection, whether we're doing exhaustively hashing or some other method. But remember that distinction we talked about earlier where we said, well, we've got two competing criteria, goals for feature descriptors. We want them to be invariant. That is, we don't want them to change very much from one image to the next at the same scene point so that I'll be able to do the match, which means you want them to the description to sort of stay the same. But what you don't want is if I've got two similar points in the scene, you want them to have two different descriptors because I don't want to match to the wrong one. That was this notion of being distinct. So we have this invariance versus distinctive. And that's a fundamental trade-off. And because of that trade-off, you have this problem that when you pick the best match, because you've done this trade-off, you are still going to get a bunch of what we call wrong matches or outliers. That is, we have some point matches that actually fit what we want, and some of them are just wrong. So the question is, what should we do? All right, so this sort of launches into the last part of this, and then hopefully naturally, because I'm such a spectacular teacher, into the next lesson. All right. So remember, why are we doing this? Well, we're trying to compute a model that aligns one picture with the other, right? We're going to compute a model that is the relationship between entities. So what we're really doing is model fitting, okay? Now, remember this picture of model fitting of lines and circles? Remember when we did that whole Huff transform thing where we were saying, well, we've got a bunch of points and we'd like to find which line is the right line or which circle is the right circle, right? And the idea was that some of our edge points come really from the circles and some of them don't. So really, that's what we're doing here, is we're doing model fitting. In order to motivate, we're going to go, let's do the math behind some simple fitting that you already know. We'll talk about typical least squares line fitting, all right? So in least squares line fitting, we're going to assume that, we've got some data points, x1, y1, up through xn, yn. All right, and we're going to use that equation y equals mx plus b because it's just easier to show what we're doing here. We had done that whole polar coordinate thing for Huff transform. We don't need to do that here. So least squares line fitting would say find the m and b that minimizes this error function, okay? And this error function which says I've got some y and I want you to find an m and b that minimizes the difference between the y that was actually measured and the y that would be predicted based upon the x value, okay? And that looks like this in the picture, all right? So the idea is that the distance that we're minimizing is this vertical distance to the line. How do we do that mathematically? Well, it's pretty straightforward. We take our original equation, and all we're going to do is we're going to essentially vectorize and matricize it. I know vectorize is a word. Matricize should be a word. It's just like a really great word. So in today's day and age, I'm going to trademark that. So if any of you use it on Twitter, you have to pay me money. All right. Here's what we're going to do. It's pretty simple. So this was our original equation, okay, where what I've done is I've turned this component into a vector multiplication, all right? And then because I'm doing this sum, okay, over the squares, what I'm going to do is I say, okay, I take this vector minus these squares, okay, that gives me what? That's another vector that is just the deltas between the y and the prediction, and I say I want the magnitude of the square magnitude, which should just be the sum of the squares. So that just gives me this very simple expression. So I go through all this mess to get this very simple expression, y minus xh, where the y here is this y vector. The x here is this matrix of the x and 1 for all the rows for each of the points. And then this h, I just use h to be the parameter for m and b. So what we have is this y minus xh squared. All right, that's our error. And what we want to do, of course, is minimize that. All right, so I just expand that out. That's what I have here on the bottom. All right, group the whole thing. I've now got this equation there, so E is equal to that. Just copy that error function over again, and we're going to take the derivative of that error with respect to h. And remember, h was just the little vector mb. If you don't remember how to take the derivative of a quantity with respect to a vector, go remember and look it up. All right, transform that, get to this very simple picture, okay, and what you have is h is equal to this quantity times y, and that's the pseudo-inverse, right? So I hope you remember that from your linear algebra. Basically, this is just the standard over-constrained least squares solution. So the model fitting has something to do with minimizing squared error, and when you work that all out, you get to the pseudo-inverse least squares solution. There's actually sort of a problem with vertical least squares, and the reason I called it vertical least squares is we're actually minimizing the error in a particular direction, right? Vertically, the y. So for example, that's not even rotation invariance. So if I get lines that are kind of horizontal, that works okay because, you know, the points. But if I got lines that are very steep, then as I move off the line a little bit, I end up with this huge error, which is not really right. I just moved off the line a little bit. And that's because I'm using this particular direction. And of course, it fails totally for vertical lines. So it's really not a good model. It's not a good noise model for what we're doing. So let's develop a slightly better model. We're going to refer to this as total least squares. And this you've also seen. So now what we want to do is we want to minimize the distance between the point, x, I, y, and some line, ax plus by equals d, where a and b are this unit normal, right? So it's actually the unit normal in the direction towards the line. So when you take the dot product of the point xi, yi, and ab, that would give you this here, okay? That should equal d, which is the distance of the point of the origin to the line. That's this distance here as is drawn there. And to the extent to which that point does not lie on that line, that perpendicular distance, as drawn here, is just ax plus by minus d, right? It's supposed to equal d, so if you subtract d, that's the dot product, and that's the perpendicular distance. At the end of the day, what that does is this gives us this new error function, e, pretty straightforward, and what we're going to do is we're going to minimize that error function now instead of our previous error function. How do we do that? Pretty straightforward. Same thing. We start with our e, all right? We're doing a minimization. We take the derivative with respect to the parameter d. That's the first one we're going to do. That generates this equation for us. We can use that to solve for d, and d is just this beautiful a x bar. X bar is the average of the x's plus b y bar. That's what these terms here are. Okay, so this now I've got an expression for d in terms of a and b. So I can substitute that back in, and I get this kind of ugly expression that we'll make beautiful in a minute. So I've now plugged these in, so there's no more d's in there. And look at that. That now looks very similar to the expression we had before, except now we've got this these means subtracted. So if I stack up all my x's, x minus x bars here, and y's minus y bar there, and I'm actually going to call that matrix U, because I do, I can write this whole thing as UH transpose UH, where H now is this parameter AB. Remember, we got rid of D, we solved for D in terms of AB, and now we just have to solve for A and B. Okay, so now that we have an expression for E in terms of U, which are known from the X's and Y's, and H, which is our parameter vector, in order to solve for H, what do? Same thing, we take the derivative of E with respect to H, repeat that equation, set that equal to 0, and that should start to look vaguely, annoyingly familiar, right? We have this matrix here, U transpose U, which is just made up of the x minus x bars stacked up, y minus y bars stacked up, transpose, whatever, times my parameter equals 0. Remember what equations equal 0 are? Those were homogeneous equations. Aha. All right, so the solution to U transpose H equals 0, well, the dumb solution is set H equal to 0. We said that wasn't going to work. Remember when we did the essential matrix and when we did calibration and all that stuff? We said, no, since we have everything okay up to a scale factor, what we're going to do is we're going to set the magnitude of H equal to 1. Now, in this particular case, we were going to do that eventually anyway, because remember A and B, which is what H is here, were the components of the unit direction of that line. So A and B have to be a unit vector, so we might as well just set the magnitude of H equal to 1. And so remember how you can solve that? You can do that whole SVD eigenvector thing again. So given U transpose U, you can find the eigenvector with the smallest eigenvalue, and that's your solution for H. I'm showing you this as a way of talking about that the right thing to do is perpendicular least squares. Here's how you do perpendicular least squares. And now the question that you really should be asking is, why is perpendicular least squares the right thing to do? Well, it's because we have in mind a particular model of noise. The model of noise we have, and we're going to refer to it as a generative model, because I have a model of how the noise is actually put within the system. Essentially, we have a particular model that we believe in. Computer vision, you have to have faith. The model that we believe is there's actually some real line underneath, and that each point has been perturbed off that line, here it's written as epsilon, by some Gaussian noise that has moved you off that line. And the probability of a Gaussian goes down by a function of what? X squared. So if you wanted to find the most likely solution, you would want to find the points that make the data that you're observing most likely. So those would be the ones where the sum of the square distances are the least, because, and just thinking about the Gaussian, won't go into too much detail, if you assume all those points were independently done, so the probability of getting all those points is just the product of those probabilities. The product of those probabilities is the product of all those Gaussians. Those Gaussians go e to the minus x squareds. When you multiply all those e to the minus x squareds, right, you just sum up all of those x squareds. And so whatever makes that sum of square difference the smallest, right, will be the highest probability. And so there's a whole bunch of assumptions going on underneath here in terms of the probability distributions and being independent and all that kind of stuff. But basically this idea of minimizing the perpendicular least squares comes from this idea that closer points are more likely, right? It's more likely a point will land closer to a line than further away from that line if the point actually came from the line. Got that? That's very important to remember for our next lesson. All right, so that's written here in this equation. Basically, we're saying the point xy that we actually measure is just some real point on the line, uv, okay, that has been perturbed in the direction perpendicular to that line, AB, that's the line that we were solving for, and the perturbation has been some amount of noise that came from a Gaussian with zero mean and some standard deviation sigma, or variance sigma squared. So for the line fitting, or in this case, model fitting generative, this is our underlying generative model, that it is a Gaussian perturbation. It turns out that that works fine when you actually have Gaussian noise. Turns out it doesn't work so great when you have some very, so we say, non-Gaussian noise, okay? So here in this picture, I've got a bunch of red points, and fitting the line through those points, okay, not very exciting. Actually, I probably should have had those points spread out. This is a problem when you steal some other people's slides. You say, you know, I should have spread out those lines a little bit. But even with all of those points sitting right on the line, okay, I'm going to add one more point, all right, just one. And it's not going to be a nice point. It's going to be if it were a Gaussian point, it would be very hard to get far away. Let's suppose my points actually are made up of a bunch of points that are perturbed by the Gaussian off the line, plus evil Megan came in and sprinkled a few just nasty points. What would happen? Well, here's just one nasty point, bang. This one point out here makes this line the quote, best solution for all of those points. Now, many of you have seen this before for robust fitting. Bear with me. That point is one of our outliers. It doesn't come from the model that we have. And our model is actually made up of two parts. Our model is that there's a line and that there's a little bit of Gaussian noise added, that there's Gaussian noise added to the points off the line. This model is the evil Megan model, and we don't even know about that. But we would like to sort of be immune to the evil Megan model. So the question is, how can we do that? And you know, why is the evil Megan model so annoying to us? Well, the real problem is that squared error, right? So the bigger the error gets, you square its effect. that heavily penalizes outliers. So outliers can have much more of an effect on our model fitting than we really want them to have. So the question is how to deal with that. So one way of dealing with it that we're going to just talk about today, we're going to do it differently next time, is what are called robust estimators. And robust estimators say, instead of minimizing the sum of squares, okay, instead we're going to try to minimize some function rho. And rho is going to be a function of two things. R here is for the residual. It's the delta. It is how far off the point is from your model. So for fitting lines, it's how far away the point is from the line. So that's our error that we were using before, and before we were just squaring that. We're going to do some other function, and it's also going to have a scale parameter sigma, okay, or a robust measure parameter sigma. There are lots and lots and lots of robust estimators. We're not going to talk a lot about them. I'm just going to show you one example because it works very simply. So here's one. This is rho as a function of u. U is just going to be that residual, that error. And here's my sigma parameter. And the function that I'm going to minimize is just going to be u squared over sigma squared plus u squared. So let's think a little bit about how that function works, what it looks like. So this is just this function y equals x squared, okay? So for y equals x squared, you can see that it grows really quickly as x grows, and that was the problem that we were trying to fix. Let's think about what happens for small values of u versus large values of u, okay? So if we pick some sigma squared, when u is small compared to sigma, sigma squared plus u squared is about sigma squared. So that means the entire function is approximately u squared over sigma squared. So that just grows by u squared the way our original function did. And so it looks kind of parabolic to start with. But what happens when u becomes really large? Well, when u becomes really large, the robust estimator here becomes almost u squared over u squared, or 1. And that's what this u is here, out here. Okay? So the idea is, as your error grows, it starts going up as a quadratic, just like our regular mean squared error, or just like our regular sum of squared errors. It goes up quadratically, but then it starts to level out. And that's what you're seeing here, is it comes up and it levels out. Now, where it levels out, that's a function of what the sigma is. Okay? So for a very small sigma, it levels out quickly. For large sigmas, it levels out much more slowly. So here's an example. Remember, we're going to, here's the same set of points. Aha! We have now foiled the evil Megan point, right? So we have this point here, and you'll notice that this line goes right through those other points. It's as if it ignored this point. Now, it didn't totally ignore the point. It gave it a constant weight, but it didn't matter whether that point was here or here or here or really far away, because once that residual got too big, it got a constant weight. Points that are nearby, they have the square error weight that we had before. So this is what it looks like when you get the scale just right. This is like Goldilocks picking the first bowl the first time. Never happens. Okay? At least not when I tell my kids, because then it would shorten the story and they wouldn't be asleep yet, so what good is that? If I set the scale too small, I get this weird line, right? Well, basically what's happened is every point is giving it a constant error, and it's just kind of going somewhere near all of the points. And also, if I set my scale too large, remember, if sigma squared is too big, then it's just like regular least squares. So I get the wrong solution again. So these robust estimators are powerful, but you do have to have an explicit, not only do you have to have an explicit choice of scale, it's pretty sensitive to your choice of scale. The method that we're going to talk about next time also has some scale parameters for the noise that we have to look at, but it's going to be much less sensitive to that. All right, we're going to stop here. We've taken a brief look at model fitting as really being a robust estimation problem. So for transforms, you want to estimate the transform, and you want to be able to do that robustly. And we use robust error functions to help. But what we're going to look at next time is a more algorithmic approach to doing this. famous method actually invented by a very good friend of mine. He's older than I am, so I'm not quite that old, that we'll talk about. And what's cool is it's a little bit more computer science oriented, and this is a computer science class, so that's great. And it's nice we can use a little bit of combinatoric analysis to show exactly how good it is. And the other thing is, it is used all the time. So you can say, well, Bobak finally is going to teach me something useful. Come back next time. All right, welcome back to Computer Vision. Last time we were talking about still estimating these transforms, and we're talking about how it was a model fitting problem. And one way of doing it robustly, because we'd have some bad matches, was to use these robust error functions. And I promised you, I always deliver on my promises, that the next time we would look at a more algorithmic approach, and sort of a more CS-oriented approach. So to remind you, our feature-based alignment algorithm is first extract some features, compute some putative matches, some possible ones based on the descriptors. And remember last time we looked at this ratio of the best match to the second best match, and we said, oh, you know, that's a good way of getting rid of some of our bad matches. And then the algorithm was supposed to do the following. It was supposed to loop until we were happy, hypothesizing a transform, and I'll say actually from some matches. And then we were going to verify the transform by looking for other matches that were consistent with the transform that we had solved for. And that's really fundamentally what we're going to do today, is talk about finding consistent matches. Some best matches are correct. That is, you pull out the best one, and it really is the right point. But some of them are not. The most important thing, though, back like we did in the Huff transform, the ones that are not are just sort of random. They're voting for Mickey Mouse, Santa Claus, Donald Duck. They're not all voting for some other particular wrong transformation. Not that there's anything wrong with Donald Duck, but he would make a poor governor. Although given some of the other governors, whatever. Anyway, so what we need to do is we want to find the right ones so that we can compute the pose, the transform, the fundamental matrix, whatever it is, the model. Okay, so this is the model that we want to compute. And today we're going to talk about this algorithm called random sample consensus, or RANSAC. So to talk about how this works, go back to our simplest example of fitting a line. So here we have some points, and if I were to ask you to fit a line, you'd probably say, well, that's the correct line, that line that kind of goes through most of the points, and somehow ignores that bad point. You're going to say, aha, that's right. Remember Evil Megan? That was the Evil Megan point. The problem is, if we don't know that that's an Evil Megan point, and we actually include it in, say, our least squares fit, we were showing you that our best fit line was not such a good one. And really what's happening, before we talked about robust estimators, what's really happened is you're just not going to get points like that from a Gaussian distribution. That is such a low probability. That point comes from outside our model. And so we have to figure out somehow that it's one of these outliers that's outside of our model. So here's the main idea of this algorithm called RANSAC. Fitting a line, a model, is easy if we know which points belong to that model and which do not. At which point I wrote, duh, yeah. A little more interesting. Now, if I had proposed a particular model, a particular line, we could probably guess in a whole bunch of points which of those points come from that line or come from that model. And those are called inliers. That is, they come from the model. The algorithm random sample consensus works as follows, and we're going to go through this. Randomly pick some points to define your line or your model. Okay? Then repeat this enough times until you find a good one. And what does it mean by a good one? A good one is one that has many inliers. That is, a lot of points are from that line. And you might think that this is a hopeless idea, just randomly picking things and computing them and hoping that you can get. Well, it turns out, actually, as was shown by Fischler and Bowles way back in the dark ages of the universe, 1981, that actually this copes with a very large proportion of outliers very well. I'll also tell you that Marty Fischler was my first boss after my PhD, and Bob Bowles sort of taught me the ways of the force or of computer vision after 1981, but not that many years after. Any given model type, so whether it's a line or transform, they have what's known as a minimal set. The minimal set is the smallest number of samples from which the model can be computed. So for a line, how many points is that? Well, 2, all right? But what about transforms, when we're transforming one image to the next, okay? Image transforms are just models. So what is the minimal set of our different transforms? Well, first of all, what are we sampling from? Well, we're sampling from proposed matches, corresponding pairs of points. Okay? So suppose I think that one image is just translated of another image. So the transformation is a translation. How many pairs do I need? One. Because if you tell me where this point A is in this other image, I now know the translational shift between any 2 points. Another way of thinking about that is I need a delta x and a delta y, and you give me an x and a y match. So I know what delta x is. I do this complicated thing called subtract, and I do it on y, and that's my offset. Okay. Homography. Ooh, we talked about this. How many pairs of corresponding points do we need to compute a homography? Do you remember? Paying attention out there? 4. Megan, get it right. How about a fundamental matrix? We showed you something called the 8-point algorithm, right? That said if you had 8 points, corresponding pairs, you can compute that. By the way, it's actually 7. We didn't really talk too much about that. Do you remember when with 8 points we could solve for the fundamental matrix, but then you would sometimes end up with a rank 3 fundamental matrix, so you had to reduce it down to a rank 2. So we did that whole getting rid of the smallest eigenvalue. That's because there's actually fewer degrees of freedom. So in principle, you can do it with 7 points, but we're just going to think of it as 8 points. So the idea is, for a translation, I need 1 pair. For a tomography, I need 4 pairs. For a fundamental matrix, I need 7 or 8 pairs. This is the minimal set that it takes to compute these things. Then you can write down the general ransack algorithm. Randomly select, it says S points, or point pair, S elements of a sample set. So you form a sample by pulling out S things that you need. You instantiate your model, so you either draw your line or compute your homography, whatever it is you do. And then you get a consensus set, C sub I. And these are the points that are sort of within the error bound. So if you think of it as homography maps this image to that image. And I can see, are the points that are all these points mapped, how many of the proposed matches now land in the same place that they said they came from? That's the number of inliers. And in fact, you might even terminate this algorithm as soon as that consensus set is big enough. Or you might just repeat it for n times, and then you return whichever model gave you the biggest set. So that's the general ransack algorithm. And of course, like any other algorithm, there are some parameters to be chosen in order to make this thing work. So the first parameter is this number S, the minimal set. That's how big is the minimal set. That number is actually usually set by whatever model you're using, right? So if you're fitting lines, that number is 2. If you're doing homographies, that number is 4 pairs. So that's set by the model. A little more problematic was this distance threshold T, or delta, as I wrote in the Greek, of saying how far away from the model that you're computing is acceptable to be an inlier. So let's look at that one just a little bit. The bottom line is, in order for you to pick a threshold, if you wanted to do this sort of analytically, what you need is a noise model. And unfortunately, this noise model is not the same model as the thing we were doing before. It's not our line, it's our belief. I'll use the word belief maybe instead of model. No, because it's a model. It's a model of how we think the noise behaves. So let's go back to our line example. You remember this? So if we were just looking at a line, so let's assume that we have this real line, and that our points are perturbed by a Gaussian noise. This is the thing we looked at last time. So the distance in a Gaussian is sometimes a complicated thing. So if you have a multidimensional Gaussian, you may know about chi-squared, and and the square root of that is the distribution of the distances. In 1D, it's actually much easier. It's essentially what's called a half normal, because basically, the probability that you're d away is you can either be d this way or d that way, but d is only a positive value, so it's just twice the regular Gaussian distribution. That's what this distribution here looks like, because it says d greater than 0. All that matters is, given a noise model, you could generate a distance model. And given a distance model, you could pick a threshold. So in fact, if you have this 1D Gaussian, let's say, and let's suppose it has a distribution parameter of sigma squared, then you could set the threshold t based upon t squared. Is this number 3.84 sigma squared? Where the heck does 3.84 come from? Well, I just arbitrarily said, let's pick a threshold such that 95% of the inliers would fall within that threshold. So 95%, if you got sigma squared, then I set t squared at 3.84 sigma squared. If you wanted 99%, you'd have to make it a bigger threshold. If you're willing to remove some points, you'd make it a smaller one. But the idea is that you have some threshold. And then you're going to accept the point if the distance d is less than that threshold. You'll count that point as an inlier. Okay? Cool. All right, so let's see. We've got our number of points. We have our distance threshold t. It says what we did here before. We've got one more. The number of samples we're going to compute. Now, this is not S, the number of points within a sample, right? A sample is a set of points that it takes to compute a model. This is how many times are we going to draw a sample? How many models are we going to try and check? So what we'd like to do is we'd like to choose n to be big enough that we can't actually guarantee that we're always going to get inliers, can we? Right? Because if we're randomly picking points, etc., and unless we would exhaustively pick all, say, n choose 2, if we're just randomly picking things, it's only with probability that we can say that what's the likelihood that we got a good solution. So what we're going to do is let's pick a probability p, and what we want to know is how big does n have to be such that the probability is p, let's say 0.99, 99%, that at least one of our samples will just be made up of points that come from the correct model, right? So that's a way of saying it. If this line, I actually get 2 points that really came from the line. Or another way of saying it is, I've got all these putative matches that are and I want to compute a homography. I want at least one set of 4 matches that I test to actually be the correct homography, all right? So the question then is, can we figure that out? And in particular, it should be pretty clear. What if all the points were right? That is, all the matches were right. Well, then as soon as you pick some set of 4, you would have 4 points that are correct, and you'd get the correct homography. What if none of the point matches were correct? Well, then you could be there all day, and you're never going to get 4 that match. In between those is that there's some percentage of points that are not correct. So if the ones that are correct are called inliers, what do you think the ones that are not correct are called?
Outliers.
Outliers. So the question is, for a given percentage of bad points, for a given outlier ratio E, so E is 20%, means that 20% of your points are bad. For a given ratio, how many samples do we have to check? So what we're going to do is we're going to calculate n. And it's actually really easy. You just step right through it. So we start off with S. S is going to be the number of points in the minimal set. Okay? P, the probability of success. This is, I want to have probability of P that at least one of my samples will be a correct set of points. Now, E, we said before, is the proportion of outliers. So what's the proportion of inliers? Well, if the proportion of outliers is 20%, the inliers is 80%, just 1 minus E. Okay? All right, now we start with just a little bit of combinatorics. All right, so let's suppose I pick S of these things. What's the probability that they're all inliers? Well, if the probability of being an inlier is 1 minus E, the probability that they're all S are inliers is 1 minus E to the S. I'm assuming that there are a lot of points to choose from, so that the fact that I've pulled one out doesn't diminish things. It's a pretty good approximation. Okay, so that's the probability that all of the points in the sample I pulled are inliers. So what's the probability that at least one of those is an outlier? Well, 1 minus that. Okay, so that's just 1 minus E to the S. Okay, so if I pull out n sets, what's the probability that all n are outliers? Well, given that my sets are independent, so it's just this 1 minus E to the S, all raised to the n. Okay, so that's the probability that all n samples have an outlier. Okay, but of course, what we want is the probability that all of them are outliers. So that means they were all bad. We want that probability to be really small, That is less than 1 minus the probability of the success. So judging here, right, so if P here was 99%, 1 minus P would be 1%. We want the probability that all of our samples had at least one outlier in them. We want that to be less than 1%. So that means that we can now just substitute in, and we get this ugly expression, 1 minus e to the s to the n has to all be less than 1 minus p. Drum roll, please. We can solve for n, and bingo, there is our equation. N's got to be greater than the log of 1 minus p divided by the log of 1 minus e to the s. And I'm sure you all have deep intuitions for what that looks like. No? Okay, let's look at some representative values. So here it's just a table, and I've highlighted a couple of entries. Let's first take a look at s equal 2 here. So let's suppose we were doing fitting a line, or if we're doing a transformation, that's a similarity transform where you take two pairs. Notice that if my percentage of outliers is 50%, so half my matches are bad, I only have to choose 17 examples for me to have a 99% chance that at least one of them was the correct one. So doing something 17 times in a computer like that, that's pretty fast. If I'm computing a homography, S is now equal to 4. Even with 50%, I only have to try 72 samples. So even though I'm totally randomly pulling these things, and I have no idea which points are right or which ones are wrong, and half the matches are wrong, with just 72 of them, I have a better than 99% likelihood that one of my sets is the correct one. And in fact, even if I'm doing a fundamental matrix, all right, looking for 8 matches, I only have to check less than 1,200 of them in order for it to be likely that one of those matches, at least one, will be a correct set of matches, so the fundamental matrix that I would get would be the correct one. One thing to notice about this table is that n does not go up very much as the percentage of outliers goes up, but it does go up pretty steeply as s gets bigger. So as the number of parameters that you need gets larger, all of a sudden the number of sample sets you have to check before you're pretty sure you'll have one that's right goes up as well. Now some of you are not table people, some of you are graph people. So what I have here is a graph where I just did s equals 4, so like a homography. And on the axis on the bottom you can see the percentage of outliers. And you can see that the number of samples required, which goes all the way up here to, well, when I make 0.8, it's above 2,000. But it stays low for a very long time. And that's the really cool thing about RANSAC, is that it stays low even with a relatively high percentage of outliers. And now let me show you the thing that I just blew right past you that's even cooler about RANSAC. All right, so how big does n have to be? Well, we gave you this equation, right? N is greater than 1 minus log of 1 minus p over log blah, 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 blah. Fine. Look at that function. What's p? P is the probability of success. What's e? The percentage of outliers. What's s? The number of points in your minimal set. Notice what's not in there is the number of points in the image, or the number of features. So you may have 10,000 or 1,000 or 100 or 500 putative matches, let's say, for a transform. Remember all those red lines that were going back and forth? The number of samples you have to draw has nothing to do with the number of possible matches that you're looking at. It only has to do with the percentage of wrong ones and the size of the minimal set and how sure you want to be that you got there. So that's really great, because that means that the whole algorithm is pretty scale invariant with respect, or I should say size invariant with respect to the number of matches and the number of hypothesized points that you have. And that actually is part of the reason that it works so well. All right, so let's illustrate that here. Let's suppose I've got two pictures, and let's just, for the sake here, assume that there's just a translation. So I'm just looking for 1 point matched to 1 point. And the system has proposed a whole bunch of matches. So there's one, and there's another, and there's another, and there's another. And all of these, you and I know are actually correct, right, Megan? Right, okay. But it also proposed this one, and it proposed that one. And those are not right. But of course, only you and I know that, and 9 million people watching. Okay, but the computer, because it's not so smart, it doesn't know that. So showing you how RANSAC works, what we do is we select one match. Here's one, that blue one right there, and we just count the number of matches that agree. So 1, 2, 3, 4, 5. Okay, great. And then we take a look at the ones that don't agree. 2, so 5 out of 7. That's 70% or whatever. 5 out of 7 of them agree. Great. Okay, so we got to do it again. We pick another one. Try that one. Count the ones that agree. 1, 2. Count the ones that don't agree. 1, 2, 3, 4, 5. That's 2 out of 7. Last time I checked, 2 out of 7 is way lower than 5 out of 7. So you would basically say, aha, here is the set of matches that are right. Now, I've got 5 points matches for doing a translation. How many points does it take to do a translation? It only took 1. So should I just pick 1? No. I have 5 translations here, all of which are a little noisy. So what do? I just take the average. I could even do sort of a robust average, but you probably don't even have to at this point, right? You just have to make sure you have enough points left in order to take the average. So basically what you're doing is you're going to use ransack in order to select the points that you believe actually come from the Gaussian noise model, get rid of the outliers, and then you do an average, which is the right thing to do when you have points from a Gaussian noise model. So here's, if we were doing a homography, here would be our ransack loop. Select 4 feature pairs at random. Compute the homography, H, that's the thing that moves it from one to the other. And then what this means is take a look at the square distance between some point in the image transformed by H, and it lands someplace, and take a look at its distance from what it claimed was the putative match in the other image. And count all the ones that are less than some threshold. Just do that loop for a while, and then you keep the one with the largest set of inliers. You then compute, you don't use the old H, you compute the least squares, the best H for that set of inliers, and that'll be a much more robust estimate of the transform. One more little piece of technical detail, which is easy, and then we'll just show you some examples, and then we're going to go have a beer because it's Friday. Remember, n is a function of the probability you want of success, S, the size of the minimal set, and E is the percentage of outliers. But I don't know E, right? If I knew which ones were wrong, right, if the Oracle of Delphi told me which ones were wrong, I would have just thrown those away to begin with and just computed the thing that was right. So if I don't know which ones are wrong, I also probably therefore don't know what percentage of them are wrong. I could try to guess. So here's what you can do. You could say, here's just in words, and then we'll do the algorithm. You can guess, say, okay, I don't know, I'm going to assume that it's 50% are wrong, maybe even 80%, but whatever it is. I'm going to assume that some percentage is wrong. And I'm going to start computing some models. If I start finding lots of models where the inliers are much higher percentage than I guessed, then I'm going to adapt my belief about the outliers to some smaller value. So that's written here as an algorithm. Basically, I start off saying, I'm going to assume that everything is an outlier, and therefore I'm going to assume that I have to take an infinite number of samples. So I'm going to be here all day, or night, and weeks, and years, whatever. But not so bad. The algorithm says, how many have I done so far? 0. I say as long as n is bigger than my current set of samples that I've tried, I'm going to pick a sample, I'm going to count the number of inliers, and I'm going to guess that the percentage of outliers is 1 minus the percentage of the inliers that I've seen so far. After all, this is just my first one, etc. If that value is less than the value that I started with, and since I started off believing that they're all outliers, I'm going to get some value smaller. So if the new E is less than the one I had before, I set that value and I recompute n. So first time around n was at infinity, and then n gets lower. And I keep doing this, and what can happen is, since I only change E if it's smaller, that means n can only get smaller. So eventually my samples, the number of samples that I tried, will get bigger than the n that I need. And when I do that, then I stop. And that's a way of adapting when you don't know a priori the number of outliers that are there. Something that I didn't mention before, it's true if you have a real noise model, in terms of how the noise is distributed from measurements, you can analytically set some threshold. Dirty little secret. We almost never have a noise model. Sometimes we do, but not too often. Because we have a noise model from somebody else's sensor center. So you know what we do? We end up adjusting it to see what works. Now, not always, and certainly never in our papers, but for real, sometimes you just have to make the thing work. How about some examples? Because RANSAC is actually used quite a bit. So you guys have already seen this one, right? So here's RANSAC for recognition. This again is from David Lowe's work. And what you can see here is there are a whole bunch of matches that were correct, but here's one, for example, that was not correct. So if we were just doing, say, an affine transform, how many matches do you need to do an affine transform? Let's see. 1 for translation, 2 for similarity, 4 for homography. So affine is 3. I think they're doing affine here. I don't think they're doing full perspective. So basically, you keep randomly picking 3 points, find the affine deformation, and when you happen to pick this one, the correct one, all of these points, you can't even see that I'm drawing all these things, but I am. All of those points become inliers. If you happen to pick this point match, and this point match, you would have said that this box kind of landed here maybe. And then you would compute the inliers and it'd be hardly any. And that's why RANSAC works for the recognition. We talked about the fundamental matrix. Okay, so here, these are actually images that I showed you, again, I think it comes from Zisserman, of Harris corners detected on 2 different images. All right? And then we do the putative matches, and instead of drawing a cross, which can be really ugly, we did something else that's ugly. And again, this I want to thank Frank Dellart, who stole this slide from somebody else, and I stole it from him. So whoever is annoyed out there, go yell at Frank. He didn't put your name on here either. I think it's Andrew Zisserman. The putative matches are drawn on this picture. Okay, and instead of trying to draw them across, I'm just sort of showing this is the belief about how it thinks the points moved. And remember, this is fundamental matrix. I've got one camera, and I've got another camera, and it's a question of how the points will move in the image. Well, they should all move smoothly according to the epipolar constraint. Remember the epipolar constraint? If I've got 2 views, if you knew the calibration, I could tell you the lines along which they have to move. So these would all be moving along these epipolar lines. But what you can see here is that a lot of these things don't seem lined up. So here we have 188 putative matches done in this particular case through cross correlation. When you run RANSAC, well, now you find a fundamental matrix that has selected out these points, and you see how they all are lined up nicely. And there were 99 inliers. And here are these points, and you see how they're all lined up not so nicely, like not at all, because they're just outliers. Their matches were just noise. So this is a case where 50%, more or less, of the matches were wrong, and yet RANSAC can handle that. Here's an example from robotics. One of the things these days that people do a lot of is use point clouds. Point clouds are recovered from some form of 3D sensing, whether it's stereo or these days a lot of people use Kinect-like sensors. And what you have here is an image from a set of depth points, and you'll notice that the bunch of these objects have been colored as different things. But notice the table is not colored. The table has been removed from the objects. You might have thought the objects were removed from the table. Not really. The table was removed from the objects. How was it done? What's the shape of a table? It's a plane. So if you know your model is a plane, you say, I'm going to pick some points, define a plane, see how many points lie on that plane. If a lot of points lie on the plane, maybe that's a real plane. That's how they found the table. They used RANSAC. Here's another example. This is actually work done by a student of mine. He was doing some work for a robot seeing objects on a table and pushing them around in order to determine how many objects were really there. But the first thing he had to do was to separate the objects from the table. How did he do that? RANSAC, find the table. Here's a video stolen off of YouTube of somebody doing real-time object segmentation off of a plane. And so you can see it runs easily, effectively, and again, they're using RANSAC to define the plane. So a couple of conclusions about RANSAC. The good. It is simple in general. It is used often. It's applicable to many different problems. It is robust even with respect to a very large number of outliers. That's really the key element. And it is not sensitive to the number of points that are in the system. We had you do the Huff transform, and those of you doing the OMS, you're going to do the ransack as well. I will tell you that in general, it's easier to get ransack to work than Huff transforms. The parameters are a little more finicky than in Huff, and for large numbers of parameters, ransack just means you have to take lots more samples. And it goes up kind of painfully, but not awfully. If you remember a Huff transform, the space complexity goes up combinatorically in the number of parameters. And these days, it's easier to deal with things that require you to be fast but not big. And so ransack, you have to be fast as the numbers go up. In Huff, the memory size gets larger. So in general, making ransack work is easier. The not so good, I want to say the bad, because Barney and Bob are good friends of mine. But actually, there's a huge body of work on ransack and all its derivatives from that. It's just one of the most fundamental algorithms of computer vision. The computational time grows quickly with the number of parameters. That was the S, the size of the minimal set. Not awfully, but you know, when you start to get more than 10, you're going to be wishing you were less than 10. It's a little bit challenging if you've got like multiple planes and you wanted to find out each of them. You have to be a lot more careful with your thresholds. So it's not as good with multiple fits. It's really not so great for approximate models, right? So suppose it's kind of a plane, but not really a plane. That's a problem because now you pulled out some points, and where it's not quite, it fit a plane that's not quite the right plane anymore. So it can be kind of sensitive to when your model doesn't really match the underlying structure of what's out there. I will tell you that it's used all the time for doing things like, it says homography, any sorts of image transforms. It's also used often for doing understanding relative views such as fundamental matrices. And generally, it's used for pretty much every problem in robot vision. It's amazing to me. In fact, I see Bob Bowles on some occasion, and I keep reminding him that, I wish I had an algorithm that I see used just so often these days, because it is a fundamental algorithm for robot vision. All right, that ends the lesson on ransack, the subunit on fitting models based on features, and in fact, the entire unit on features. This kind of work, finding features, figuring out how they match, is pervasive in sort of geometric computer vision, the computer vision that talks all about how cameras align and scenes and depths and points. And so they used a lot these days because of just how ubiquitous imagery and video is. And because these methods are sort of powerful and real and not just math, they're used in lots of real applications. So I expect if you end up doing any work that involves dealing with multiple images and trying to figure out something about the relation between them, that you will actually see things like Harris detectors, things like the SIFT descriptors, and certainly things like the ransack alignment. All right, welcome back to Computer Vision. And when I say back, I took a whole week off, so basically I have no idea where we are. So hopefully you'll be more get your act together than I do. I think last time we were talking something about the Lucas-Canati method of solving for optical flow or for motion. And if you remember, we had this problem with optical flow that we referred to as the aperture problem. The aperture problem was if you look at a little local area and you can only tell the motion that is in the direction of the gradient perpendicular to the edge. So basically, to solve that, we had to impose some form of constraints. First, we did the global constraints, then we did the local constraints of Lucas and Canati. And the idea was by having these local constraints, we could have more than one equation per pixel. And the basic idea was to pretend that all the pixels were moving in the same direction in a little local neighborhood, so we would sum up over that window. We said a 5 by 5 window, you'd have 25 equations per pixel. And that basically gave us this least squares solution, and we related that to the whole Harris corners, where we said that if the matrix here, A transpose A, if that matrix was well conditioned, meant we had two decent sized eigenvalues, it meant that the gradient occurred in various directions over that window. And we mentioned how this method of recovering how something moved was first proposed by Lucas Canati in 1981. But critical to the whole derivation was the idea that we use this Taylor series expansion, that is, that we could approximate how something would move or how much the intensity would change by essentially fitting a planar ramp That's the first order derivative approximation, fitting a planar ramp to a point, and then as the point would move, the intensity would change according to the slope on that ramp. But of course, there were certain assumptions built into Lucas-Canati that were sometimes problematic. So the main assumption was that the pixel as it moved didn't change its color, didn't change its intensity. So if brightness constancy doesn't hold, then you have to do something in terms of feature detection, finding a feature from one place to another. And we've already talked about doing SIFT detection and characterization in order to do these matches. And we can combine those. In fact, we're not going to, but I'll talk at the very end about how you can combine dense estimation with SIFT estimation. The other thing we said is that possibly a bunch of points are moving one way and another points are moving another way. So in that area, within a window, you don't actually have all the points moving in the same direction. And you have to solve that with a motion segmentation. We mentioned that. We'll actually go over sort of a mechanism of doing that, not at the end of this lecture, but at the end of the next one. Oh, these aren't lectures, these are videos. So that makes them sound like they're more fun. But the most fundamental assumption of Lucas and Canati, or at least the one that in some sense is most problematic and yet fixable, is this idea that we can use that Taylor series approximation. So the idea of that Taylor series approximation is that we can make a small ramp estimate, that is a first order linear estimate, and then as things move a little bit, that'll tell us how things change. And we've gone over one method. We talked about nonlinear iterative refinement, so that if it's still the right model in terms of the point nearby is changing, but it's not linear, maybe it's quadratic or something, we use a bunch of linear successive approximations. But actually, that's not the problem that exists most often. The one that exists most often is that actually pixel motion is not small. And so you can't just assume that you can tell how things have changed by just doing a very local analysis. So to solve that, we have to do something called coarse-to-fine estimation. To illustrate what I mean, here's a simple example. So here you see on this one, on the left side, I have curves that have been shifted by only a small amount. So when I find one point value, the nearest match is actually the correct displacement. So if I actually fit a little slope through here, I can do my local estimate, and I'll eventually find the correct match. But over here, I've got a different situation. So there's one point. The nearest match will now be this red point, right? So it basically has just estimated the change to be that much, all right, where the actual shift, of course, is much, much more, all right? And so the estimated shift is too small. So the question is, how would you fix that? So let's take a look at this on a real picture. So here's an example on some real pictures. So this is 2 frames taken out of the MPEG garden sequence, and what you can see is that I've got one frame, and then in the next frame the tree moves to the left quite a bit because the camera has moved to the right. And you can see the tree in the front is including the tree in the back. Okay, so question. Do you think that this is a small enough motion to be able to run Lucas and Canati? No, look, there's a lot more than 1 pixel or a small number of pixel motion with a planar assumption between. I'm uncovering entire trees in the background, right? So the problem is, you know, how could we solve this, right? How could we eliminate this problem of large pixel motion? And I'm going to show you with a single slide. You're going to look at it. You're going to go, aha, I get it. Ready? Now.
Aha, I get it.
What do you get? Okay, here's what you got. And the top left corner is the original sequence, all right? And you can see that the thing is moving a whole bunch of pixels. I don't know, maybe it's moving, let's call it 7. On the top right, you'll notice the picture is drawn the same size, but I've actually reduced the pixels in half. So now it says there's like 90 pixels across, right? Before there was something like 180. Well, gee, if I was moving 7 pixels before, now I'd only be moving 3.5 pixels. Ah. Do it again. Now I've only got 45-ish pixels, bottom left-hand corner. Now instead of moving 3.5, well, half of 3.5 is 1 3/4. Okay? That's still more than 1, isn't it? Yes. Okay? Well, cut it in half again. So now I have this picture on the bottom right. And if you look at that animation, you'll see, you can sort of see it shifting within the pixels. It's actually less than a 1 pixel motion. Okay, it's a very blurry picture, and I had to make it really blow it up, and now you can actually see each pixel in there. But you can see that the motion is a sub-pixel motion. So basically what we want to do is we want to implement a motion recovery method that takes this coarse image and then iteratively, or I should say multi-scale-wise, goes to a finer and finer image. This is how it works. Right? So I've got my one image and my other image, which is why they're called image 1 and image 2. All right? And the first thing we're going to do is we're going to build what are called Gaussian pyramids. All right? And that's illustrated like this. So it's Gaussian pyramid of image 1. We'll talk more extensively in a minute about how you might go about building those pyramids. This is just notionally so you understand what's going on. So now I have these reduced pyramids. At the top level, remember I have that very blurry picture that actually only has a small number of pixels in it, and the motion between them is actually much smaller. And that's shown here, right? So here it says U is 10. So that's saying, let's suppose the shift is 10 pixels at the lowest level. Well, when I cut it in half, it becomes 5, then it becomes 2.5, then it becomes 1 1/4. I can keep going. So this is how I reduce the amount of motion that's present. So because I've reduced the amount of motion, I can first run Lucas and Canati between those coarsest level. And I might do the iterative thing. That's the thing we looked at last time, where I fit it plane, estimate it, shift it a little bit, estimate it, shift it a little bit, keep doing till I converge. So that will map the motion between the very reduced image 1 and the very reduced image 2, right? So I can compare that. I can find the motion between them. The question then is, what do I do next? Well, what I have to do is I have to go from the coarser to the next finer level, okay? And what's written here is warp and upsample, all right? We're going to go through the details of that, but basically the way you can think about this is I compare something at a coarse level, then I know, okay, if I were to double up this image and double up that image, I'd have to double up the motion field. I'd also have to double the amount I'm moving. We'll do that algorithm in a minute. But I could apply that to the next level, and what that will do is that will get me the next level very close to the second image at that level, and I could run Lucas and Canati again. And then I can iterate and run that over again and eventually get the entire motion field. Couple things to show you. First, let me just show you that this kind of works. All right, here's some optic flow results taken from a computer vision class, 2003, from actually a tutorial here, listed on the bottom. And you can see that when you run Lucas and Canati on that front tree without pyramids, you get sort of terrible results. And voila, when you run it with the pyramid, you get a much better result. And our goal is to be able to get that much better result. But before we can do this, we have to talk a little bit more about multiple scale. So we've been having all this multiple scale stuff. Now, this isn't going to surprise you that it relates to some of the aliasing stuff and frequency stuff that we talked about, oh God, feels like months ago. It's probably months ago. I have no idea when it was. Anyway, when we were talking about Fourier analysis and different scale. And what we're going to do now is take a little detour through multi-scale, and then we'll come back to Lucas and Canati. All right. So we talked about aliasing, and now I want to show you aliasing in terms of image subsampling, okay? So image subsampling is what? We talked about, you just throw away some number of pixels. So here we have a nice, I sure hope it's in public domain, picture by Van Gogh. This is one where you can see his ear. So on the other side, I guess there's no ear. You know about that, right? I'm going to assume you have some experience with Van Gogh. Anyway, okay, fine. So the picture on the left is an original picture where I've thrown away every sample. Maybe you can't tell. Picture in the middle, I've thrown away every other sample again, both horizontally and vertically. The picture on the right, I've done it again. Even I can tell, you probably can't tell, I can tell it's kind of looking kind of crummy. And in fact, if I blow up that picture on the right, I see this, okay? And what you're seeing here, the junk that's in here is caused by this aliasing, just like we talked about last time. And when I zoom it back up, you can see that you've brought these high frequencies in there, and there's all this stuff in here that just doesn't seem like it's the blurry version of what was in the original. And that's because it's not. It's an aliased example. So how do we handle aliasing? Well, we talked about this last time. What we have to do is we have to filter and then subsample. So what I've done now is I've taken a small Gaussian smoothing the original, subsampled, then smooth it again and subsample, then smooth it again and subsample, and now when I blow it back up, you'll notice that the Gaussian sample down, that actually looks like a blurred version of the thing on the left. Okay? And that's because I haven't done any aliasing. So to do this multi-scale stuff the right way, I have to sort of do this blurring and subsampling.
All right, let's do this in code. Write a function to downsample an image to half its size. You can do this by picking alternate rows and columns. Now write another function, this time blur and then downsample the image. Here is a test image. I wonder how long you can sit on that at a time. Okay, to relieve that guy of his misery, let's downsample the image. This should be half the original size, that is half width, half height. Once more, and a third time. Let's do the same with the blur and downsample function. Alright, now we have two images, 1/8 the original size. Let's view the downsampled image, magnified to the original size. And let's compare that with the other image. Implement the two functions and compare the results. You know what they'll look like. The first one is very easy. Octave and MATLAB make it really trivial to specify indices repeating at a given step. In this case, we would like to start with row 1, step 2, and till the end. Exactly the same for columns. This selects rows and columns 1, 3, 5, and so on. Okay, now for blurring. Remember how we used IMFilter? Pass in an image and a filter defined here using the fSpecial function. As mentioned, we want a Gaussian of size 5 by 5. Alright, so this is our filtered image. We simply use the same indexing as before. Make sense? Let's see what it looks like. Alright, here's the result of only downsampling. And this is with blurring and downsampling. This appears to be a more natural, blurred version of the original image, whereas the former has ugly aliasing effects. Note that the result is being affected by how the resize function works. You can control how it functions using a third parameter. Here, passing in nearest means no interpolation. As you can see, this is a much more accurate representation of what the pixels in the 1/8 size image look like. By the way, this is the downsampled image. Compare this with the blurred and downsampled version. It still wins. You can also use linear or bicubic, which is the default. Try these out. We'll be using downsampling to build Gaussian pyramids next.
Imaged pyramids, the phrase was popular back in the late 70s, early 80s. Paper that made it really famous was the Burton Adelson. Same Ted Adelson that I showed you an example of from before in terms of some visual illusions. And they built something called a Gaussian pyramid. And a Gaussian pyramid is just this reduction, just like I told you before. One of the things we can do with Gaussian images or these reduced images is we can also create something called bandpass images. And having this ability to do both Gaussian and bandpass lets you deal with scale very well, which is why I want to show you this a little bit here. So what you have here is, it says Gaussian pyramid, and it is a Gaussian pyramid, but it's blown back up again, all right? In fact, remember these pictures where I'm showing you the different Van Goghs, and it says half resolution, quarter, and eighth, but they're the same size? That's because I blew up the eighth size one back up to the original size, so you could see it, right? So it would look the same way, all right? So here, I did the same thing. This is our Lena picture that we talked about before. And this is the original, then blurred and subsampled, and then blown back up again. Blurred, subsampled, blown again. So these are the lower and lower resolution images. What I can do is, I can subtract one picture from another to get this difference. All right? So this is a difference image. Two things. First of all, this is called the Laplacian, and you should know why. If you remember when we did the detections, and we first did Harris corners, and then we talked about the SIFT detectors, David Lowe was talking about using extrema points in scale space. And we said, well, one of the things you could do is you could run a Laplacian over different scales, or you could take different Gaussians and subtract them. Those were the difference of Gaussians. And difference of Gaussians was approximately the same as a Laplacian. That's why these images are called Laplacian images. Okay? They're also approximately bandpass. And we talked about this just a little bit when we talked about Fourier analysis. But the idea is that the lowest frequency, if this is frequency here, has a fall off like that. So the next one, if it had higher frequency, might look like that. And if I subtract these two, basically I'm mostly going to be looking at that space. So this is the power of the frequency. And so when you take a Gaussian blurred image and you subtract from that another Gaussian blurred image that's close but not the same amount of blurring, you get this section of frequency that you're looking at. It's not totally bandpass because stuff leaks out this side and stuff leaks out that side, but that's why they're called, in quotes, bandpass filtering. So these images here, these are called the Laplacian images. What's kind of cool about the Laplacian images is you can actually use them to reconstruct the original image if you have one thing. So what's that one thing you have to have? You have to have the power. No. What you have to have is the smallest of the original blurred Gaussian, the top of the Gaussian pyramid. Reason I have to have that is if I take this and I add back in this, I'll get this one. Here, let me draw in Lena here like that. Put her in her hat and her eyes and her nose. Yeah, there she is. All right. Well, once I have that, I can add that to this and get a finer version of Lena. And then I can add this and get back the original. Okay? So the Laplacian pyramid plus the coarsest of level from the Gaussian pyramid allows me to do reconstruction. All right. Keep going on this a little bit to show you how to do the construction of the Laplacian pyramid, because you're going to use exactly the same steps for building a Laplacian pyramid you're going to use to run hierarchical Lucas and Canati. That's why we're doing this, so we can get over here. You got that? Good. Here is an awful picture. But its picture comes from the paper, and it'll show you what we're doing. So this is our original picture, I equals G0. And in Laplacian pyramid, the 0 level is the finest level. And that way, you always have the 0 level, and 1 would be filtered down once, level 2 is filtered second time, level 3. And you can filter as many times as you want to, up to n, or n being some big number. Okay, but the idea is you start at 0. Sometimes people don't like that. They typically want the 0 to be the most compact one, but that doesn't make any sense because Ted's a really smart guy. He wouldn't do that. You start with your original image as 0, and then you keep filtering it down. All right? So that's our original image. The first thing we have is this reduce operator. Okay? And we're going to go over these in some detail. But the reduce operator essentially takes a Gaussian, that's the convolution signal, blurs it, and then this down arrow here means downsampling. So just taking every other pixel. That would give you level 1. Do it again, you would get level 2, et cetera, et cetera, et cetera. That one's sort of straightforward. And like I said, we'll go through the numbers in a minute. The one that's a little less clear is the expand operator. Remember, we have to expand these things up. So if I expand up the coarsed one and then I subtract that from G1, that gives me L1. That gives me the first Laplacian. All right? The expand operator is a little less intuitive than the reduce operator. Let me show you what they are. The reduce operation is pretty clear. So the idea is at this level, we have a full resolution or whatever level, and then we want to take the next level down. So here's a way of thinking about it. We'll just number these. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 pixels across. I actually don't have to produce the pixels that would go under 2, 4, 6, and 8 because I only want half the number of pixels that I had to start with. So in fact, what this does is it simply says I'm going to take some location, here I use the middle, and I'm going to take what's called a 5-tap filter, and here are the filters. See, it's 1/16, 4/16, 6/16, 4/16, 1/16, and that's what these numbers are. 1/16, 1/4, 3/8, 1/4, 1/16. Okay? That's the filter that I use to get the odd pixel here in the middle. Now, that's just in one scan line. I'm working with images. How do I do this? Okay, go way back in your notes, because I know you're all taking copious notes. I almost said y'all. When I say y'all, Megan's going to throw that monitor at me, okay? Nothing against my friends from the South, but I come from New York, went to school in Boston. If I actually said y'all, I think I'd get shot by my relatives. Anyway, you all have seen this before. We talked about separable filters, right? So a separable filter was, instead of applying a square filter or a 2D filter, I apply one-dimensional filter horizontally, and then often it's the same one-dimensional filter vertically. So go back up and remember about separable filters. The reduce operator uses a separable filter, a 5-tap separable filter, first in the rows, then in the columns. All right, that one was straightforward. The expand operator is a little bit trickier, and you can tell that by looking at this awful picture. In fact, I'm going to pull that awful picture out by itself. Here's the deal. The idea is that on this picture, only pixels that were real. The question is, how do you make finer pixels from a coarser level? So here's the coarser level, here's the finer level. And it turns out you do it 2 different ways, okay? So we're going to start with the odd pixels, all right? So the odd pixels occur underneath pixels that are actually there. So there are a couple of ways of thinking about this. One is, we're just going to assume that I'm just tell you what the filter is, right? That it's 1/8, 3/4, 1/8. Okay? That seems a little bit arbitrary until you realize that's just kind of like if these were zeros, okay, and I took in all the values here and I made it the same 5-tap before, but now doubled it, so 1/8, 1/2, 3/4, 1. These would be in the same ratio of 1, 4, 6, 4, 1 as before, okay? But I'm only pulling it off the odd pixels, all right? And so these points go away, and I'm only left with 1/8, 3/4, 1/8. By the way, we're going to provide the original Burt and Adelson paper that talks about reduce and expand, so you'll be able to look at that a little bit more carefully. All right. That's to reproduce a pixel that's actually underneath one that's there. Slightly trickier are the even pixels. We have a pixel here that's underneath something that didn't actually exist. So if I still do the 6, 4, 1, right, 1, 4, 6, 4, 1 above me, okay, well, when I'm on one of these even pixels, there's nothing directly above me, and there's nothing to my ends. There's only these 2 here. That's this one and this one. So looking 5 above me, only 2 of them are really there. They're equally distant from me. What coefficients am I going to use? I'm going to use 1/2. So to produce this finer value, I take 1/2 of that pixel and 1/2 the other. And that actually sort of makes sense. If you think about it, if I'm blowing up a picture, so I'm going to go from, say, 7 pixels to 14, I have to get space between 2 pixels that were there. What value should I put in that space? Halfway between the ones that were there before. Okay? The one that's a little trickier to understand is if I'm blowing it up, how come I just don't leave this original pixel alone? And you can read in the paper, this is for the odd pixels, you can read in the paper the motivation in terms of frequency theory in terms of how they do that. All you need to know is that you now have a reduce operator and an expand operator. You want to see something cool?
Yes.
Okay. Let me show you how come they got their paper on the cover. I think it was the ACM. I think it was a journal of the ACM. I forget. They had the cover picture of a journal, and here's why. Here's a picture of an apple. Okay? Beautiful picture of an apple. Here's a picture of an orange, and I'm going to tell you it's not just any picture of an orange. You'll notice that this apple is in front of some pencils, this orange is in front of some other pencils, kind of same colored background, and you'll notice they're the same size, and that's because they've been scaled to be the same size. Using the Laplacian pyramid stuff, I can make this picture. Okay, now if Megan could see this picture, Megan would be going, wow, how did they do that?
Wow, how did they do that?
Okay, first of all, I hope you are too. It's pretty cool. It's half orange, half apple, and it blends, and you can't see any seams. All right? And the way they did that is they built a Laplacian pyramid. So this is the coarser scales. This is the original Laplace scale, the coarser. And they just seamed together each one of the pyramids by just a single pixel, but at the small size, not the expanded size. So at the very small one, they took half of the left half of the apple, the right half of the orange, and they just blended the middle row. Then they expand that, okay, take the Laplacian here, Laplacian there, combine that, add in with single row. You do that all the way down, and what you've done is you've blended the low frequencies over a larger range of the image and the high frequencies over a smaller range, and you make this magic apple orange thing. And that's how you get yourself on the cover of the transactions on ACM transactions on graphics. Cool, right? Now we're going to apply these pyramids to Lucas and Canati. So here's another really, really ugly picture. And what I'm going to do is I'm going to step you through the algorithm in a minute, but let me just show you sort of in drawing, okay? So first is, here's our image at t minus 1. Here's our image at t. We reduce and we reduce on both of these in order to get small versions of them. The first thing we do is this M stands for motion model. We run Lucas and Canati between those two, okay? And that gives us a flow field, okay? And what we do is we make, and that tells you how every pixel moves, we double up and multiply by 2 that flow field, and then we apply that to the next level down. And then there's this funny function called warp. We take that function, we warp the level 1 of t minus 1, and now that's almost the level 1 at time t. It's almost there. So you know what we can do because it's almost there? We can run Lucas and Canati again, right? We come up with a new motion field, add it back to the motion field that we had before, expand up, multiply by 2, apply and warp, and continue. And that's how the iterative Lucas and Canati algorithm works. I know that that's hard to see from a picture. Here is the algorithm written out as steps. So we're going to compute to level k, right? So we build all of our Gaussians up to level k. We initialize the flow field as being 0 at sort of k plus 1. Then what do we have to do? Well, you know, here we're doing it from level k to 0. So from the previous level, we have the flow field from the previous level, which of course is half the size. So we have to upsample the flow field. That's just expand it, make it twice as big, all right? And that's now the right size to map from level k to level k of t minus 1 to t. The problem is, if in the previous level something moved by 1.2 pixels, how far is it going to move now? 1.2 times 2, 2.4 pixels. So when I expand the flow field, which just makes it a bigger size, I also have to multiply it by 2. That's what the next step of the algorithm says, is multiply UIP and VIP by 2 to get the predicted flow. And then you warp that level of the Gaussian of image 2 towards image 1 in order to get 2 prime, or t minus 1 to t. Whether you call it 1 or 2 doesn't matter. And you just keep iterating, and then we apply Lucas and Canati again between the warped version and that same level of I1 to get this slight, what's called the correction flow. And we have to add that correction flow back to the expanded flow that we had before. That's what these equations here are doing. They're adding that slight difference that we now found back to the original predicted flow. Here are some results. So this is an example of the optic flow, and here's that tree. And you can see if we don't do it hierarchically, we just apply Lucas Canati, it does a nice job on the background, but up on the tree itself, where there was a large amount of motion, it gives you exactly what you'd expect, which is junk. But when we run it with the pyramids, we get a better solution. And so you get these nice, flow fields here in the middle, also in the back. Now you'll notice we still have a problem at the boundaries, right? And why is that? Well, remember, at the boundaries, there are pixels appearing and disappearing. And there's no way that optic flow knows what to do when a pixel appears out of nowhere. Basically because you moved and now there are pixels that were invisible before are now visible. And so the optic flow along the occlusion boundaries is still a problem. And you need further processing to handle that. All right, so that's hierarchical Lucas and Canati. And as we described it, it gives you a dense flow field. It gives you a UV at every location. But remember, we said that we might only want to do Lucas and Canati at areas where the eigenvalues were well behaved. That is, the places that are kind of corner-like. So there's a version of Lucas and Canati called sparse Lucas and Canati, which is just that. It's a hierarchical version that's applied only to what they call good locations or good features to track. This actually comes out of some work by Shi and Tomasi and good features to track and applying Lucas and Canati to it. And by the way, those of you who use OpenCV, the Lucas and Canati used to be dense, And then they just changed it. It's now actually sparse. So now it only gives it to you at a select set of points. And they sort of changed it without telling you because the function still compiles. It just, your code just breaks a little. So, so you should only be using the sparse version. All right, so look, what I'm showing you here was sort of the state-of-the-art of motion estimation 20 some odd years ago for derivatives. And for a first class where you're starting to do this, that's fine. We're not assuming you have any background in computer vision. But if you were to actually take a look at work that's going on now, you will find motion estimation that takes this as the basis and then it adds a lot of other stuff to it. So they worry about sort of how the gradient behaves, the constancy of the gradient. They have energy minimization terms. Remember we did energy minimization for stereo, and that came up to be a better solution. It not only had the local matches, but also had a more global structure to it. It also does key point matching, which is saying I've got something that has moved a long distance. So remember, the short distance, the expansion works really well. We have to do things hierarchically to get the long distance. Or you could just use point to point, right? I know this point went over here. Let me fill in the stuff behind it or around it. And when you do that, you get sort of a much better result altogether. And this is an image taken from a paper that came out in 2009. That ends the lesson. I was about to say that ends the lesson on Lucas-Canati flow. That's pretty much true. It's only a little bit of a lie because we're going to see a little bit more of this derivative motion stuff in the next lesson. But basically what we did is we solved for a different flow at every point by assuming that a window over that point had a particular flow everywhere. And then we move the window a little bit, and now we pretend that in this new window the flow might be something different, even though those windows overlap, which is a little strange, but that's how you do it. So it's okay to have small errors along the way like that. But the idea, there's a little bit of a contradiction here, right? In fact, that contradiction is in what I just said. We assume that a window is all moving the same way around a point, and we assign that value to that point. Then we move the window a little bit, and we throw away that last thing, and we say, we're going to assign it to the next point, even though those windows overlap. You might say, I want to carve the image up into sort of coherently moving patches. And so there's two parts of that. There's this notion of how do I do the carving up, and what do you mean by coherently moving? And what that means is you've got a model for the motion inside these regions. And the next lesson we'll talk about motion models and how we could find regions that behave according to some motion model. All right, welcome back to Computer Vision. Today and next couple lessons, we're going to spend just a little bit of time on sort of the whole light reflection process that results in photons essentially hitting our camera or our retina. The idea that this is how the physics of the imaging or the creation of the light that the imaging is going to make a picture of. And there's actually a huge amount known about this area, and it all comes from both sort of material science, where we study the materials, but the big motivator has been computer graphics, right? Computer graphics, the idea is I have some model of an object and its surface type, and I have some model of the light, and I'd like to produce an image as if you were actually looking at the real object. So to do that, I have to understand how light interacts with these objects. Now, in the old days, and when I say the old days, I mean like 20 to 40 years ago, there was this view that computer vision was just inverse computer graphics, right? I mean, computer graphics, you have a model of the object and a model of the light, and you make a picture. And computer vision was thought of as, well, given a picture, can you tell me about the light and the object that's there? And so there was a lot of focus on recovering image surface properties and object properties and lighting conditions as sort of an inverse problem. And to do that, we had to have a lot of understanding of the physics of how images were formed. Now, more recently in computer vision, a lot of what we talked about here, there's been more of a focus on really the geometry of sort of where features get located, and that relates to sort of the shapes of objects and the relation. And you didn't have to worry quite so much about the precise physics. And then also a lot was saying, let's lump all together the lighting, the shape, the texture, the imaging, the camera, etc. We just get out pictures, and we use machine learning or recognition techniques to trying to do labeling. And we talked, and when we will actually be talking about that in the future. But it is it's still important to understand something about how the physics of light works with respect to making images. So here's a sort of toy or a schematic, right? So the general idea is that we've got some lighting, all right, and the lighting hits objects. And so we need physical models or models of the physics. And the idea is that that causes light to impinge upon whatever your photosensitive system is, whether it's a retina or a CCD or CMOS or whatever your imaging technology is. And then, of course, that's the picture that we're going to take a look at in the computer. So there are all sorts of physical processes that impact the image that you're going to see. So, here's a picture. I think actually this might be from Mark Polyfice. Don't remember. Here's a picture, two pictures, and it's pretty clear to you what's going on here, right? That we've got this sort of textured stuff everywhere, and that there's differential light falling on it, right? That there are these shadows. And so when you look at that, you probably don't think that that's a texture painted on the surface of the road, but rather that that's a shadow on a more uniform texture. But of course, it could have been painted, so your brain has to be doing something in order to understand that. And this white tape that's shown here is just a little bit showing you sort of how things appear to you, right? To you, it's clear that this is a thing that's on the ground, right? That is not part of the texture of the ground, but is something else. So you've said, okay, that's one thing that's reflecting one way, and I've got some other object, namely the asphalt, that's reflecting another way. So that's sort of lighting surfaces and shadows. Of course, there are reflections, right? So in both of these window pictures, you're probably guessing that there's not like this thing here that's behind the window, and maybe it's just a reflection of what's behind you. Likewise, you can see in this tree, it's all distorted a little bit because maybe this glass isn't so perfect, but the idea is that you can see this reflection, and that reflection is impacting the image that gets made. Going along with reflection is refraction, right? So it's most easily seen in things like water or various kinds of deformed glass. So here, these wavy lines on the bottom of the pool, well, there are no wavy lines on the bottom of the pool, at least I hope not, but instead the water itself is no longer flat there. There are some waves, and that's causing the light rays to bend in a particular way. So again, that impacts the image that you see. This beautiful picture here has got both reflection and refraction going on inside of it. An interesting property, which is really, it's just about reflection, is what's referred to as interreflections. And both of these pictures are drawn from computer graphics. It's not so much about the nature of the surface, but what impacts the light that you see at a point. And sometimes we tend to think of, well, there's just some light source and it's illuminating our objects. Well, there's been a lot of work done sort of since the 90s on what's referred to as interreflection, both in computer vision and computer graphics. So here when we have these shiny materials, you can see everything being reflected within it. But I think a more subtle example is this is the famous graphics teapot being rendered in a variety of ways. Now, of course, in a shiny surface, you know that you're going to see a reflection of this purple teapot in front of it. But also in these partially reflective things, you see this purple color in there that's reflective of this purple pot that's in front of it. So the idea is you have all this light bouncing around, and all of that light can impact what's actually observed at a particular point. In computer graphics, there's a method called ray tracing, which basically, as rays of light come in and they bounce off, they create illumination at all these different facets of the model, and you can get a really rich rendering. One of the things that's a little different in computer vision today than before is, traditionally when I taught computer vision, I could assume that everybody had taken graphics, because there was sort of this connection between graphics and vision. These days, it's much more likely people will have taken machine learning, because there's a view of computer vision as a data-driven inference problem, and people are less likely to have taken a graphics course and understand the physics that are here. Computer vision draws both from understanding what's going on from data, but also having built-in models that have to do with the nature of the physics. Then there's things that happen to the light between bouncing off a surface and entering your eye. So here's an example referred to as scattering, where this is what the picture maybe should look like if you think of it as being very clear. But if you actually just took a look at the raw image, you would see this because of moisture and other particulates in the air and the wavelengths that are absorbed, that the light changes as it comes through. And in fact, there was a really cool paper done about depth from what's called the dark channel, which basically says that, the further away something is, the harder it is for something to be black in your image because there's a little bit of fog all the way through. So they actually estimate the depth of the scene based upon essentially the amount of fog-induced lightness that's there. And this is all from an understanding of the nature of the physics. And there are lots of other phenomena that impact, the light that comes in. Here's fog and water dripping and all sorts of different types of effects. So what we're going to talk about today is essentially the surface appearance of objects. And what we mean by that is, the question is, if I've got some surface element and it's being illuminated by a source, what is it that the sensor is going to see? And the idea is that the image intensity is going to be a function of a couple of things. One is the local shape, and we can think of the shape as just being the surface normal of a little patch. Then there is the surface reflectance, that is, what are the properties of the surface that affect the light? And then there is the illumination, that is both the direction and the type of light that's coming in, sort of its intensity, maybe its wavelengths, and those kinds of things. And the amount of reflection that will be observed is a function of both sort of the incoming direction and the outgoing direction and its relationship to the surface. And we're going to make that a little bit more formal going forward. So now we're going to do just a tiny bit of nomenclature with respect to the physics. It's a little bit confusing, and later we'll drop some of it, but it's important to get just a little bit of a basis. So the general area of considering light is sometimes referred to as radiometry, which is the idea of measurement of light. And the first term that we talk about is the radiance, okay? So the radiance is always some light that is being carried by a ray, or sort of, you can think of coming off of something or out of something. In a minute, we're going to talk about the irradiance, which is the amount of light falling on something. All right? So the radiance is sort of energy, as it says, is energy carried by a ray. And what I want you to do think about is, assume there's like this little patch out here that's of a sort of a fixed angle that's observed down here at some point. And this angle, this little patch, we'll call d omega. All right? So radiance is measured as power, the amount of energy per unit area, but the area is measured perpendicular to the source. So if this is our little area here, okay, but our light source is over here, we'll make our little sun there, okay, and this is a little patch of the sun, what we actually have to think about is the area perpendicular to that ray. And so because it's perpendicular, we measure, this is going to be a little weird, we measure the amount of radiance in this funny unit called watts per square meter. So that part's okay, right? It's watts per, you can imagine watts per square meter of that little disk, but it's per what's called steradian. Well, you know what a radian is, right? A radian is a measure of angle. A steradian is a measure of solid angle, right? So this is this little cone, this is a cone funneled out, right? And the steradian is the amount of angular area of that cone, okay? Because if I had some big sort of extended source here, you'd have to integrate over all of this different area, but we're only going to use this little delta omega patch. And like I said, in a minute we'll simplify this whole thing. But just this idea is that the energy that's coming from that thing is a function of, so I have to think about how much light is falling on my area as a function of the amount of different area that I can see up there, right? So one is the area down here, and the other is the amount of the source that I can see, and that's measured in steradians because it's the solid angle. The irradiance, sometimes called energy E, that's the energy actually arriving at the surface. Okay, so now we're going to talk about the energy at the surface. Okay, so now I've gone back to, and I'm going to leave both this perpendicular part and this is the area on my surface. Okay? Now, it's because I'm actually looking at my surface, I'm just going to measure that as the power per unit area, so that's just watts per meter squared. Okay? So clearly, there's this relationship between the amount of energy hitting that perpendicular part and then this skewed, the area on the surface. And the easiest way to think about that is to think about this as a foreshortening effect. All right? So here we have a light source. And the idea is that this is the direction of light, and this area, this card here is meant to be perpendicular, right? So there'll be a certain amount of light falling on that card, right? But if the card was not perpendicular, right? If the card was tilted away, then the same amount of light now gets spread over a larger area. And so it's foreshortened. So in other words, we get less light per little unit area from that light source. And we can write that down in the following way, sort of for a surface receiving some radiance from some direction, coming from this, we'll say, fixed little patch d omega. The corresponding irradiance, the light landing on the surface, is just the radiance modulated by this angle, right? So as that angle gets closer and closer and closer to pi over 2, 90 degrees, the amount of irradiance goes down to 0, which is right because you're essentially spreading the same amount of light over a much bigger area. So that sort of talks about the energy, and now what we have to do is we have to talk about what is the relationship between the light coming in and the light going out, because the light going out is the light that's going to go into your sensor, all right? And to model that, we use what's called the bidirectional reflectance distribution function, or BRDF, okay? And the idea of the BRDF is that I've got a little surface patch that has a normal, and my light comes in at some angle, and I'm going to be viewing it at some other angle, all right? And I want to talk about the amount of sort of the proportion of this light that comes in as sort of what proportion of this light coming in this direction goes out in some other particular direction. By the way, this angle theta here, that's the tilt angle. That is the amount that you're off of the normal. And then there's a rotation around the normal. That's the phi, okay? And for some surfaces, we actually have to worry about both of those angles, all right? And so the irradiance is the amount, just as we said before, it's the light per unit area that's coming onto the surface. And now it's radiance, because now it's not the radiance from the light source, it's the radiance back from the reflecting surface. Okay, remember, radiance is the stuff coming out, irradiance is the stuff landing on it. So now we had this, before the radiance was the stuff coming out of the light source, now the radiance is the light coming up off the reflected surface. So we'll just write this as E of the irradiance of the surface in some particular direction. The L is, I don't know why I guess we use L for radiance sometimes because it's actually the lightness of what you're going to be seeing. That's the radiance from the surface in some particular direction going out. And the BRDF, the bidirectional reflectance distribution function, is just the ratio of those two things, right? So it's the percentage of the light reflected as a function of the light coming in. Okay? A couple things about it is that obviously you can't reflect more light than came in, so that ratio is going to be less than 1. Now you might get a very bright spot in some direction if it were to integrate over all these different lights, but from one particular direction, the most I can do is send back all the light. I can't manufacture light. This is a passive system here. There are a couple of cool little properties of the BRDF. One, named Helmholtz after the guy Helmholtz. Basically, light doesn't know which way's up. Or another way of saying it is, it's a reciprocity. That is, that if the light source is coming this way and the camera's going that way, and I swap the camera and the light source, I get the same reflectance function, right? So it doesn't matter whether the light comes in this way and goes out that way, or comes in this way and goes out that way. There is no light diode for the nerds among us, all right? There probably are, you probably could build active light diodes, but for normal properties, we don't get that. For our purposes, there's another important property, which is referred to as rotational symmetry. And the way of thinking about that is, if I rotate the surface about the normal, nothing's going to change, all right? And what that essentially means is that I only have to worry about the little tangent plane right at the point that I'm looking. And so the only thing that matters is the relative direction between these, not just in terms of, here I want to talk about the amount around the angle. So the absolute angle doesn't matter, just the relative distance between them. And that's written like this. The absolute angle in terms of the tilt still matters. Okay, and we'll show you that in just a minute. But the rotation around is only relative around the normal. Bidirectional reflection distribution functions for real objects can be incredibly complicated. Here's a sort of little panoply of different types of reflectance functions. We're not going to talk any more about those. If you want to take a computer graphics course and learn how to render hair or It's just one down here, by the way. I think that's a peacock feather. That's actually not dye, but it's refractive. So bird feathers actually are not painted, if you will, but they refract the light through the material that's in it. It's a very complicated BRDF. We're not going to talk any more about that because we're going to talk about two specific reflectance functions that are special cases of BRDFs, and that you can combine them to sort of make most normal types of objects. And namely, we're going to talk about what's called diffuse or matte reflection plus specular reflection. Let's talk about reflection models. Here we have our surface, okay, and we have our incident light, and it's coming in. And it's coming in some particular direction, and this will be some theta I, which is going to be the tilt off of the surface normal. The first physical process I want to talk about is referred to as sort of body reflection. And what happens is the light comes in, and it sort of scatters around at the top part of the surface, and then it comes out in lots of different directions. And therefore, it's impacted by the stuff that's in the surface, all right? And that's referred to as diffuse or body reflection, okay? And it tends to have what's referred to as a matte appearance and some sort of what's referred to as non-homogeneous sort of particulate matter have that kind of reflection. So this example here is this clay pot. If you think of this clay pot and you look at it, in some sense there's no shininess to it at all, right? It's purely matte. It's purely diffuse. And in particular, we'll talk later, no matter what direction you look at it, it seems to be approximately the same brightness. It turns out it's actually pretty hard to make purely matte surfaces. Like if you take matte spray paint and you spray something, even then there's sort of a certain amount of shininess to it, which we'll get to in a minute. But the general model that we're looking at of body reflection is the light comes in, is scattered about in the medium of the surface, and then goes out in a variety of directions. So that's the body or diffuse reflection model. So what else can happen to the light? Well, the other thing that can happen to the light is referred to as a specular reflection. Okay? So a specular reflection, just like you think, some of the light before we saw it penetrates down, etc., but some of the light doesn't. It just bounces straight back up. Okay? And that's referred to as surface reflection. And surface reflection is a specular reflection, and it's responsible for sort of the glossy highlights that you see on shiny surfaces, and in metals in particular. So here's a picture of a variety of things. This one, by the way, is a fake picture. That's to show you the highlights. But for example, shiny metal things, this metal pot. Here's an interesting one, right? Here's a can that clearly has stuff painted on it, right? So that's affecting the light coming in. It scatters around and bounces out. But you see also that there's this stripe here, right? Well, that stripe is the specular component of what's there. By the way, if you want to study more about specular things, the reason it works in metals, it has to do with the way the light interacts with the electrons that are in the surface. And that's part of what, makes metals metals, or these free electrons. Go take a look at your material science stuff. But those sort of atomic physical properties have an impact on how light behaves when it hits the surface, all right? And that's your specular reflection. And the general overall view of the universe is that the image intensity can be thought of as a combination of the body reflection plus the surface reflection. Okay? And as a reasonable model for what's going on, we can sort of model most surfaces as having a certain component of body or matte reflection plus specular reflection. Let's talk about now a specific mathematical model of body reflection. Remember before we said it comes in, bounces around a little bit, and then scatters out. Okay? So the model we're going to talk about is called Lambertian model, or it's a Lambertian BRDF, but we'll just think of it as being Lambertian, all right? And we're only going to talk about the body reflection part. And Lambert's law, Lambert being the guy who did this, the sort of folksy way of thinking about it is that no matter how I look at it, no matter what direction of reflectance that I have, it looks to be the same brightness. That is, the only thing that's going to impact this is the incident component of the light. Not notionally, the more perpendicular the surface is to the light source, remember the radiance and irradiance thing, right? It gets more of the light, and therefore the brightness will only be affected by the angle between the surface and the light source. Now, most people not most people, some people will then show you a picture that looks like this. And by the way, if the person who made this picture is listening, I'm not saying that you didn't understand what happened. I'm just going to say that most people, when they see this picture, think the following, which is not true. Okay? What they think is that, depending upon the light source coming in, the more perpendicular it is, the more light you have reflecting out. That is true. But what's drawn here is that the amount of light coming out is the same in all directions. That is just not true. Okay? And by the way, I want to thank Bertolt Horn, who, by the way, invented the shape from shading problems and most other computer vision problems way back in like the 70s and 80s, because I took my first computer vision course, and he made a big deal about this. And you see that, Bertolt? I was paying attention. What actually happens in Lambertian shading is the following, okay? When the light is reflected out, basically it falls off, so it's sort of equal area here. So you see that this amount, so more light is reflected perpendicularly out than is reflected sideways, okay? And in fact, as you fall off, this thing goes down by the cosine of the angle, so that actually almost no light at all goes out sideways. So a lot of light reflects back up, and almost no light at all reflects sideways. So you might ask, get ready, Megan, well, why does it look equally bright from all directions?
Well, why does it look equally bright from all directions?
I love it when stuff works. It's that same foreshortening effect, but this time it goes the other way around, right? If I've got sort of a pixel having a particular angle, so that's what this is meant to be, a pixel having an angle. When I look down through here, it has a smaller area, it's drawn sort of wrong here, than when I look this way. Think about it this way. If I had a camera out here, the same angle, right, would now get a much bigger area coming into the same pixel. So if I understand the math right, and I think I do, what this means is that the amount of area that I see in the surface grows by the cosine of that angle, or I should say 1 over the cosine of that angle. So as that angle gets smaller and gets closer and closer to 90 degrees, right, I start to see an infinite amount of patch in the same little pixel. But over here, I'm putting out smaller and smaller and smaller light. And these cosines, in fact, here they are here, this one and that one, they cancel. And that's why it looks equally bright from every direction. So I think I got that right. I'm sure my computer vision colleagues are going to send me email or just make fun of me on the web if I got that wrong. But I'm pretty sure that's the way it works. What you need to know is that it appears equally bright from all directions. Here we're back to our diagram where we've got our incident light coming in, light going out in some direction, and the surface appears equally bright from all directions. That is, it is independent of your viewing direction. All right? So one way of thinking about this is that the BRDF of a Lambertian surface is simply a constant, and that constant is referred to as the albedo, and here it's just written as rho, and this is the rho sub d for diffuse. By the way, often when this is written, you'll see a cosine theta I in the denominator, and that's for compensating for this viewing condition, but I think that just makes life confusing. So we're just going to think of the BRDF as being a constant for a Lambertian surface. And so what that means is that the surface radiance is just going to be that constant times the source intensity, I, times the cosine of the incident angle, right? Because the irradiance is a function of the radiance of your source times the cosine of that angle, and then the thing looks equally bright from all directions. So that's usually written this way as just the magnitude of the source times the albedo, and you can write this as the dot product between the normal and the incident direction, right? It's just the dot product, the cosine, between the normal of the surface and the angle of the light coming in. And that's what's referred to as Lambertian shading. Here's an example of, again, a fake sphere, Lambertian shaded. And the idea, of course, is that, when it's pointing in the direction of the light source, it's brightest, and then it falls off by the cosine of that angle. Okay, so that's the matte component, the body component. What about the specular or the mirror component? Now, of course, in a real mirror, and you all learned this in high school physics, right? There's only a reflection at the perfect mirror angle. Remember, angle in equals angle out? I'm sure you learned that somewhere in your physics class. Well, so using our diagram again, what this says is that all the incident light is reflected only in a single direction. Okay? And I'm going to call that direction M for the mirror direction. And here we have V for the viewing direction. Okay? And so that light is only going to be visible when V equals M. All right? So I have to be in the, so if I've got a point coming from right here, I'm going to see it right there at that point. And everywhere else, it's not reflecting over that. I might see it at a different point, but all the light is being reflected along a particular ray. All right? And so the BRDF is just what's called a double delta function. If I'm thinking about this on my surface, right, this angle down and the angle out has to be equal. But this is drawn difficult. It's in 2D. Not only do they have to be sort of at the same tilt, but they have to be in a plane, right? In other words, this and this have to be in the same plane. Because if I were to rotate it this way, all right, then it would now be bouncing off in another direction. And so that's why there's two angles. This is the tilt angle, and this is the rotation around angle that says basically one has to be pi opposite the other. So we take this BRDF and we stick it into our radiance equation. And what it says is that the radiance, essentially the brightness that we're going to see out, is the magnitude of the source intensity. The rho sub s is the specular reflection. So, for example, it might be a darkened glass that filters out some light, so it still acts as a mirror but only reflects some percentage of it. That's what the rho would do. And then we have these two delta functions, okay? And these two delta functions say that basically the angle in terms of the tilt has to be the same, and also the rotation around have to be exactly pi different. That's what those two things say. Now remember, the delta function is a function that if the argument is 0, it's a 1, otherwise it's 0, and that's why it's written as a delta function. So I want to abuse the notation just a little bit, and I'm going to say, well, I can also write this as saying that the radiance in this particular case, same as before, but now I'm using, I guess, what I'm calling a vector delta function, right? So what we said before is that I only see a reflection if the viewing angle is exactly the mirror angle, right? So essentially, these two things would have to be the same so that I'm lined up in exactly the right spot. Another way of writing that is that the half angle is the same as the normal, right? So another way of saying that is if the vector that's exactly halfway between the sensor and the light is the same as the normal, then you get a mirror reflection. And that would be for sort of a single perfect point. So that's the mirror BRDF. Most things that are shiny are not perfect mirrors, but we can think of them as being glossy, okay? And what the glossy means is, if we have our illuminant here and we're coming out some angle, it means I don't have light just at the mirror point, but it's spread out a little bit, okay? And that's what this lobe here is meant to show, okay? And the more gloss, as opposed to being specular, right, blurrier, I make that lobe a little bit fatter. Okay? And that's written as this equation, which says that basically, now instead of doing that delta function, I just take the cosine of the angle between them, all right, m dot v, raised to some exponent, okay? Because that's the angle between them, and I raise some exponent. Now, if the angle between them is 0, that means it's the perfect mirror angle, right? Then that dot product is 1, raised to a k, it stays 1, and I get a perfect reflection. But as the angle falls off a little bit, cosine becomes a little bit less than 1, and when I raise a number less than 1 to the k, well, as k gets bigger, that falls off faster, okay? And in fact, you can see that illustrated here. These are some artificially generated images. So here it's just, moving the light source to different directions, okay, not so exciting. Here, you can see that the specular component is getting tighter and tighter and tighter. All right, and so it's getting more like a mirror, and that's the raising of that k. Okay, and so that's the specular component. And in computer graphics and in computer vision, what we often do is we combine that diffuse and the specular, and it's referred to as the Phong model, because Phong was one of the first people to do it. Then there's the Blin-Phong model, and there's lots of models that have increased beyond that. But the idea basically is you say that you can model the BRDF of lots of surfaces as a combination of a Lambertian plus a specular. So we have the Lambertian, which is the, everything looks equally bright from all directions. That's what these equal-sized arrows are meant to show you. Remember, the light doesn't go out equally, it just looks equally bright. Plus the specular model, whose sort of blur amount is defined by that fall off. And when you combine those, you can get sort of the matte plus the specular. And here's an example of some recovered imaging where here you have a original image, and here you've sort of broken it down into the matte components and the specular components. Likewise here, you have this object that has the matte surface, that's the paint itself, plus the glossiness of the varnish or whatever it is. What is it you put on top of ceramics to make it glossy?
Gloss?
Gloss. Thank you very much. Okay, and the idea is that this is the matte component, and again, this is the specular component. And the ability to pull those out is a computer vision problem. That's all the physics we're going to do. We've talked about how we model the light, and we talked about surface properties, so the albedo of the matte reflectance and sort of the specular component. And we've talked about how the shape, the surface normals, interacts with that. So in computer vision, there are these fundamental questions of, well, when I look at a scene, can I figure out, say, the shape or the albedo or both just from an image that I'm looking at? And so fundamentally, this is an ill-posed problem, right? Because it's an interaction between both the shape and the whatever's painted or the texture on the surface. And yet our brain does it all the time, which means that we as computer vision scientists, we'd like to try to do it too. So over the next couple of lessons, we'll be talking sort of the computer vision approach to recovering those elements. Okay, welcome back to computer vision. This is going to be our third lesson having to do with essentially how intensity and shape and light interact with one another. In the first one, we talked about the physics in terms of how that interaction works. In the second one, we talked about what if you want to try to recover something about the surface properties of the object, the reflectance function. Basically, you have to make some assumptions about the shape or the illumination. Well, today, we're going to turn it around the other way, and we're going to say, well, how can I recover something about the shape of the object based upon what I'm seeing? So this general area of work was actually started by, I guess, probably Bertolt Horn and maybe some others, but I certainly learned about it from Bertolt way back in the 70s, then continued in the 80s and 90s quite a bit. It's referred to as shape from shading. And the idea is, so over here you see a picture of a real sphere this time, right? And you can tell that this is a sphere, right, with a light source over here. Likewise, you can tell that from this person that probably this is the front part facing you and that the shape tapers off. Likewise, you can tell from the shading here something about the texture and the shape of the face. And the question is how to use shading as sort of a cue for recovering the shape information. So in order to talk about shape from shading, or I'll call it shape from lighting, because one of the things that we're going to do in a little bit called photometric stereo is not so much a shading variation as it is from having multiple light sources. What we have to do is we have to look at the relationship between the intensity that's seen by the camera and the actual shape of the object. Now, that means we have to look at that reflectance function. Remember what we defined, I guess, 2 lessons ago about this interaction between the surface normals and the light direction and the surface itself. And in particular, we're going to introduce a mathematical construct referred to as the reflectance map. And the reflectance map will be the basis of a lot of what we'll do today. So necessarily, we have to introduce a little bit of notation in mathematics in order to make it easier to understand what this reflectance map is. So we're going to start by assuming we have a surface Z of x, y, right? So here we have Z in this direction, x and y in that direction, and you have some surface. As you move in, say, the x direction and the y direction, your z value changes. And in fact, you can talk about how z changes as you move in x and y. That would be the partial derivatives of z with respect to x and respect to y. And we're going to define 2 variables referred to as p and q to represent these derivatives. Now, there's a little bit of ambiguity in the literature. When I learned it from Bertolt, P was the partial of z with respect to x, Q is the partial of z with respect to y. As I was rummaging around the web to see how people talk about this, all of a sudden sometimes people use the negative of the partial of z with respect to x and the partial of z with respect to y. And it turns out when you do it as the negative, it makes some formulations a little bit easier. So I'm going to use it as the negative, but you can use it either way as long as you're consistent. So let's assume we have some sort of a surface normal. Okay, so here we have our surface normal drawn, and it is on a surface. Okay. If we have a point on a surface, we can define two tangents, all right? One is, if I take a step just in the x direction, there's a question of how does z change. So if I step in the x direction, no change in y, then my change in z will just be the partial of z with respect to x, and so that's negative p. So tangent in the x direction, so it's on the surface. Let's draw ourselves a little surface here, put a point here, and this is one tangent vector. Okay? Well, the other tangent vector we can have is if we just take a step headed in the y direction, then there's how the z changes as a function of y, and that's negative q, and so that would be another tangent. So if I want to find the surface normal, that's easy to do. I just take the cross product of those two directions. By the way, these vectors, they're not, I haven't made them unit vectors or anything, they're just taking a step that goes one in the x direction and changes however much it does in z, same thing for the y. So if I want a unit normal, what I have to do is I have to take tx cross ty. So I remember the cross product of two vectors is perpendicular to that, right? So I take tx cross ty, and if I want it to be a unit vector, I have to normalize it by the magnitude, okay? And so when you take tx cross ty, you get pq1, and the magnitude of that, of course, is the square root of p squared plus q squared plus 1. By the way, so the reason I use the minus partial respect to z respect to x and y is that allows my normal to be pq1. If I did it the other way, it would be minus p minus q1. So it's the same difference. So that's the algebraic description of P and Q, and that's important because we're going to use it. But it's also important to understand the geometric interpretation, because when we reason about multiple constraints, it'll be easier to think about that. To do that, I have to introduce something called the Gaussian sphere. So here we have a sphere, and the idea of a Gaussian sphere is it represents all possible surface normals. So suppose I have a shape, and I'll just draw some sort of shape here like that. It's kind of a potato-looking thing, right? If I have some point here, it has a surface normal in some direction. Well, that surface normal is right here on the sphere. And likewise, if I had a normal here, that one would be right there on the sphere, okay? So there's a mapping from all the surface normals to the Gaussian sphere. And in particular, if I have z as a function of xy, and I'm only worrying about things pointing up, then essentially only the top half of that sphere do I have to worry about, right? So there's going to be a relationship between every normal and a point on the Gaussian sphere. So the PQ space that I was just talking about is actually a projection of the Gaussian sphere. And the way it works is as follows. Imagine, and I'll draw this in 3D in a minute, but here's in 2D. Imagine I have an origin at the center of the sphere, and I come out at the location of that normal, and I hit a plane that's located at the top pole of the sphere. So here I'm showing it in 2D, just makes it a little bit easier, but actually to look at PQ space, we have to look at this in 3D. So here the idea is, here's my little normal, it was there, and it points up until it hits this plane, and that location would be P0, Q0. All right, for this particular normal. And this z equals 1 plane up here, that's sometimes called the gradient space or the PQ plane projection. And the idea is that every normal has a PQ value. So I can represent normals just by their PQ value. And so now we're going to use that to define our reflectance map. Got it? Cool. Let's suppose I have two vectors. So I'm working from a point. I've got two vectors. I've got a vector S that's in the direction of my source, and a vector N that's in the direction of the normal of the surface. All right. Well, those vectors are whatever they are. Their unit vectors are sort of small s, small n. So remember, I can project any vector up onto the PQ plane, and that's what this is. This is at the z equal 1 PQ plane. So I've got a PQ for the normal of the surface, and I've got like P sub s, Q sub s for the vector that is in the direction of the light source. So when I write that, I get the following, right? Remember we said that our unit vector n is just PQ1 divided by the magnitude of P squared plus Q squared plus 1 square root of. And likewise, the unit vector in the direction of the source is just PSQS1 divided by its magnitude. All right? So far, so good. So we have an algebraic representation of both of those normals. So let's suppose for a moment we have a Lambertian surface. Then the only thing that determines, in terms of the geometry here, the amount of brightness that we see is just this angle I, which is kind of lost in this mess here. But there it is. It's the angle between those two vectors. And what I need to know, of course, is the cosine of that angle, right? That's the Lambertian surface equation. Well, given all of this algebra, we can represent that cosine as follows, right? The cosine of that angle is just the dot product of those two unit normals. So it's the dot product of n, dot product of s, which is the dot product of these quantities, which is written right there. Okay? So that is the representation in PQ space of what that cosine of that angle is. So now we're ready to talk in general about the problem of shape from shading. So the basic problem is this. Given, say, one, maybe more, but for now one image that looks like either this top image or the bottom image, can you, the computer, recover for me a function z of xy? So that's why it's going to map onto this gradient space nicely. So we're imagining that we've just got a single viewpoint. You can think of z as coming towards me, and I want to know the height of the function as I go over the image. By the way, this is just one representation of depth. It's a very viewpoint-specific representation of depth. If I had multiple cameras and I had different viewpoints, then the notion of z as a function of xy would not be a great representation of the geometry that's out there. And in fact, much later in the class, we'll talk about other depth sensors and things like point clouds, which is a different way of representing geometry. But for here, we're just talking about z as a function of xy. So the fundamental question is, given this single image, can we recover the 3D shape? Well, as we talked about when we did lightness, fundamentally this is an ill-posed problem, right? Because I don't know what the underlying albedo is, and I don't maybe not know what the illumination is. So there could be lots of different shapes and combinations of illumination, albedo, that would give the same image. So, as I said, this is ill-posed. In order to solve this, we have to make some form of assumptions. And those assumptions can be the lighting is known, so I know the direction of the light. Maybe I'm assuming that it's Lambertian and that it's the same albedo everywhere. That would be an example. Or maybe I say that I know what the boundary conditions are. What we're going to have to do is we're going to have to bring in some other kinds of assumptions to make this work. So what we're going to do is, in order to figure out how to go from an image to the shape, we're going to talk about this reflectance map. So the reflectance map relates the brightness I of xy. And again, I'm just going to talk about sort of the brightness in the image, assuming that the image is linear with respect to the light that's hitting it. So I'm not going to talk more about radiance or irradiance, etc. I'm just talking about the lightness or the brightness of the image. All right. So the reflectance map relates the image brightness to the surface orientation, remember PQ, for a given source direction and a given surface reflectance. Okay, so this assumes, for the moment, that you know the source direction and you know the surface reflectance. Let's first consider the Lambertian case, all right? So here we have our same math again. We're going to assume that we've got some source brightness, which we'll just call K here. We have some surface albedo, rho. And we're just going to use our same equation as we had before, that rho times K times the cosine of the incident angle, right? That's the angle between the source and the normal, is what's going to determine how bright our image is. And what we're going to do for the next little bit is we're going to assume that just rho times K equals 1. Or another way of saying it is we're just going to assume that our image intensity is the cosine of the angle. You could make it proportional to the cosine of the angle, but the idea is that it's a fixed number. In fact, later we are going to assume that it's proportional. Clearly, what matters in the brightness that we see is this angle, the incident angle between the normal and the light source. All right, so here is the mathematics of our Lambertian system. And in order to try to keep everything straight, I've sort of color-coded. The normal is pinkish, purplish, magenta. Is that fuchsia? Yeah, I don't know. I don't really know my colors. And this sickly green or bluish, I don't know, some color. So we got sickly purple and sickly green, but just keep them straight, all right? But the idea is the purple is the surface normal, the green is the direction towards the illuminant. So the dot product that we showed before is just P times PS plus Q times QS plus 1 over the normalization, and we refer to that as R of PQ. And this is the reflectance map in this Lambertian case. Okay, so this R of PQ. So what is that going to look like in PQ space? Well, to figure that out, we can actually just do it algebraically, but it's actually kind of cooler to do it geometrically. All right. So here we have our light source, and we have some vector pointing up to our light source. Now, if my normal is some theta I away from it, that means that it is in some cone around that light source direction, right? So for some constant cosine of I or some constant theta of I, that's a cone around the illumination direction, all right? Well, I can project, remember, PQ space allows me to map any direction, any surface orientation, to a PQ location, right? So I'm going to project that constant cone up into PQ space, and I'm going to get this elliptical, it's not really an ellipse, I'm just going to get this cone sliced by a plane. And the idea is that everywhere along that curve is the same cosine angle between the surface normal and the source direction. So that means that it's equally bright. Those are referred to as isobrightness contours in PQ space. That's a lot to say. But basically, along that curve in PQ space, I get the same intensity because that curve represents the set of possible angles that are the same cosine theta away from the source direction. Look at that a little more carefully in PQ space. Let's assume that we've got some source PQ that's right here. All right? So if my surface normal were pointing right at that direction, so the theta I is 0, cosine I is 1, then my value would be 1. All right? But suppose cosine is 0.9. All right? Well, that would be some curve, draw it around here, right? This is some isobrightness contour, so every one of those PQs would give a intensity of 0.9. Going out a little further, 0.8, 0.7, gets even further out, 0.6, 0.5, right? Here's all the way down to 0.3. And then finally, what happens when we get to a point where the surface normal is perpendicular to the light source? Well, if the surface normal is perpendicular to the light source, the cosine of theta I is 0, so no light is hitting that surface, okay? And so that would be this line here, right there, where it's a 0 value, because that's the equation of a line in PQ space, right? P times PS plus Q times QS plus 1 equals 0. That's like AX plus BY plus C equals 0 in the P, but it's in PQ space, so it's AP plus BQ plus C equals 0, so it's a line. So the perpendicular situation is a line in PQ space. So, and notice, by the way, that the R of PQ is a maximum right when the surface normal lines up with the light source, as you might expect. So that's our reflectance map in the Lambertian situation. How about shape from a single image? So given R of PQ, so that means that we know where the light source direction is and we know the surface reflectance, so we can eliminate that or assume it equals to 1. Can we determine PQ everywhere, the surface orientation, uniquely for every image point? So here we have, some random point, and maybe its intensity compared to the brightest point is 0.7, so it's somewhere on that curve. But it's somewhere on that curve. I don't know exactly where it is on that, in that PQ space. So no, I can't sort of just simply from this analysis be able to determine the total shape or the orientation at every location. So if I want to do this, if I want to compute shape from a single image, how might we do that? Well, basically this is an example of an ill-posed problem, and we need some additional constraints. We need some additional information, like the lighting is known, or boundary condition, or maybe even other information. And in fact, there are sort of two standard moves to make. Basically, one that doesn't really work and one that does. The one that doesn't really work, which we'll talk about in just a minute, was the traditional shape from shading, and that is we're going to add some additional constraints. And the one that does work is you actually take more images with different light sources illuminated, and that's called photometric stereo. That has some real applicability. So let's first talk about traditional shape from shading, where you add more constraints. Remember, here is our question. Given a single image of a known surface reflectance, so we know the albedo, with a known light source, can we recover its shape? As we said, that means given that RPQ, can we determine PQ everywhere? And the answer is, well, I have to cheat a little. No, not cheat. I have to make some assumptions. Assumption number one is that, for example, at this boundary, which is already drawn in red, I'll do it again, we're going to assume the shape is known. And in fact, what you can imagine is that everywhere at this boundary, because it's falling off, I know that the surface normal is 90 degrees from the camera. So I know something about the surface orientation. Then the other thing that I'm going to assume is that the surface is integrable. What that means is, remember, I'm recovering orientation. Well, orientation you can think of as the surface derivative. Well, the whole thing has to integrate to a depth value. Okay? And then finally, I'm going to assume some sort of smoothness, and I'm going to put this whole thing in some form of an optimization method. Back 100 years ago, I did a paper with Yvonne Leclerc called Direct Height from Shading, I think it was called, which attempted to not do it quite so much in a orientation-based way, but directly in a height way and take the derivatives. It was, we were running on a connection machine. But basically, the idea was to recover the full height from this image under these relatively restrictive assumptions that you know the albedo everywhere, that you know either the depth or the orientation at some particular contour. We actually used stereo at the contour to get that initialization, then we did shape from shading in between. If you look up shape from shading, you'll see a lot of pictures that look like this, and these are typically synthetic results. So given some depth map, you can make some sort of a shaded image, and then you can show that you can recover the shape that's really there. Unfortunately, one of the reasons they show synthetic results so much is that the results on real images are somewhat, shall we say, less than wonderful. In fact, there was a paper by Mubarak Shah and some students, I think in the late 90s, early 2000s, where I think the phrase was something like, well, it works poorly in the lab and not quite as well as that in real life. You know, basically, and why is that? Well, the problem is these assumptions are overly restrictive. I mean, a constant albedo everywhere, that means you get no variation in the color or the underlying texture of what's there. You know, knowing about the light source, the orientation directions, it's a very brittle type of computation. So what can we do instead? Well, what we can do instead is we can take more images. All right. And this is what's referred to as photometric stereo. So the idea is that we take picture from the same camera location. So we can still have Z as a function of X, Y, same object, but with different lighting. So here we have the picture taken from the same location with different lighting directions. And what we want to get out is this, right? The Z is a function of X, Y. And unlike traditional shape from shading, with enough lights and sort of careful calibration, etc., we can also recover the albedo, the reflectance function at every point. So now we don't have to make this overly restrictive assumption that the color or the reflectance of the object is the same everywhere. We're allowed to let it vary. Let's go through this algebraically. So here we have our camera, which has some viewing direction, all right? And the viewing direction is not going to matter because we're going to assume a Lambertian system, which is what we have here. We assume that it's just proportional to the cosine of the incident angle between the light source and the normal, but the idea is that the camera is fixed. And for each one of our sources, source 1, we take our first image. Source 2, we take our second image. Source 3, we take our third image. Now notice, by the way, that rho is in these equations, right? Rho is the albedo, so I'm not assuming I know the albedo. So now I have 3 images, right? And I can write these as a matrix equation for, this is for a single pixel, right? So at a single pixel, I would have 3 different values, and I could just write this equation as rho, and these are the 3 vectors that are the source directions. And by the way, I assume I know the source directions, times the unit normal, and the unit normal is the thing that I don't know. So I need to solve for that, all right? So remember, we're making this Lambertian assumption. So solving those equations is straightforward. It's linear, it's a simple linear system if we have 3 lights. I is our 3 measurements, 3 intensities. S are the 3 directions to the light source, and we know those, so I and S are known. And then, as we said before, N is supposed to be unit normal, rho is the albedo, so together I call them N tilde. So to solve for N tilde is trivial. N tilde is just S inverse I. But of course, N tilde is not a unit normal. In fact, its magnitude is what? Its magnitude is the albedo, so I can solve for rho, the albedo, and I can solve for the unit normal as well by just taking the magnitude of that. Now, of course, that's with 3 lights, and anything that works well with 3 lights is going to work better with more lights. So let's suppose we have more lights, like m of them. Well, we get the same set of equations, but now we need a least squares solution because the system is over-constrained, and basically solve it here. So m by 1 is the number of measurements we have, and so we have to take the pseudo-inverse. And the pseudo-inverse will give us the least squares solution for N tilde, and then again you can find the albedo. That was the algebraic approach to the solution, and it works nicely. In fact, that's the math that you would actually encode if you were writing a computer program to do this. But what it doesn't do is give you exactly the intuition of what's going on in photometric stereo. So to do that, let's take a look at this in PQ space. So let's suppose we have some light source, the first light source PS1, QS1. And so we'll say that, remember, we know where it's located. And then if we measure its intensity, let's say it's 0.7, that's some particular curve here. So the other ones are dotted to remind you of them. But the idea is that the solution for P and Q must lie somewhere on that curve, right? We don't know where yet. So what do? Well, in the old shape-from shading, we did some funny sort of assumptions and integration and stuff that just doesn't work. Well, here all we do is we say, let me put up another light source. Here is a second light source, PQ of 2 of S, and now it has to lie somewhere on this curve. Okay, you'll notice those curves intersect in more than one place. Well, that's troubling. It intersects more than one place. What do we do to make it come to one place? Well, we just put down a third light source. All right? And if everything is calibrated and working correctly, then the orientation of that point and the albedo are recovered at being exactly that location. So that's the geometric sort of description of photometric stereo. A simple example is shown here. Here is a sphere. You can sort of tell that it's a sphere, right? It falls off down here, so we're looking straight down, with 5 different illuminations. When we do photometric stereo on that, remember, we can recover both surface normal and the albedo. And that's what this looks like here, right? So the albedo, you can see that it recovered the fact that it's got these 4 quadrants. So even though this thing falls off slowly, it knows that it's all the same albedo. And then this is the estimated of the surface normals. And so this is what's sometimes called a needle diagram, where you're looking at where the needles are pointing. That's the surface normal. Now you can actually do this somewhat for real. So here's an example where there are 4 input images, so the lighting is coming from different directions, right? You can see here you get different kind of shading, right? And it recovers both the albedo, which is sort of the paint, the color, and you can see that it actually knows that there are these stripes on there along with the surface normals. So it recovered the shape. In fact, there's a really cool app you can download from this company called trimensional.com, and this is not a commercial endorsement, it's just a Georgia Tech endorsement. This was an app put together by Grant Schindler, where you basically take your, I don't know if he's got it on Androids now as well, but certainly at the time it was on iPhones, and you take pictures from different locations, and it uses the light to illuminate it, and it does a surface reconstruction. All right? And it works pretty cool, and download it, and I think it's it might be free. I know it might be $1. Maybe it's $4. Whatever it is, if you buy it, Grant, send me money. Okay, so photometric stereo is used in a couple of interesting applications. It does have some challenges, like you have to know the reflectance function. You have to know that reflectance map. So typically it's assumed for Lambertian types of stuff, maybe a little bit of specularity, but basically you have to understand the reflectance function. It also has a problem with shadows or inner reflections because it's assuming that the only thing that matters was the orientation of the surface with respect to the light. There are some smaller problems, like the cameras and light sources have to be far enough away that it's a constant angle. That's not so bad. Calibration is important, right? Remember, we're assuming that everything is linear in terms of the intensity with respect to the light that's hitting the camera. So you need a lot of photometric calibration. Before I conclude, a couple things about some shape from shading. One is there was a really cool use of it. There was a paper, actually won one of the Marr prizes in 1995 in ICCV, and it was this idea. The name of it is Shape from Shading with Inner Reflections under a Proximal Light Source, Distortion-Free Copying of an Unfolded Book. And it appeared later in IJCV, International Journal of Computer Vision. And what they were looking at was this idea that, you know, when you put a book down on a scanner or a copier, you get this surface that bends away. And you can recover something about that surface structure, and you should also be able to sort of unshade what happens because the light falls off. Now, unfortunately, the images that are in the original picture don't reproduce very well, so you're going to see something that looks really ugly here. Obviously, it wasn't pure black in here, but it was just very darkened, and they were able to recover the white in the text by essentially undoing the shape from shading. And I thought that was pretty cool. Shape from shading also, in the human world, of course, is much more complicated, a whole bunch of interesting effects. One that's well known is this light source direction effect. So if you see here on the right, you probably see, especially if you're looking at this sort of vertically, you probably see a sphere lit from up here. What most people see, if you show them just this thing on the right, is a dimple, something pushed in, okay? With, again, the light source coming down. Now, of course, figure B is just figure A rotated around. So on one, you see something bent out towards you. On the other, you see something pushed in. But the reality is they've just been rotated around. There seems to be a human preference for light sources to be up above instead of down below. And there's a whole bunch of other work on sort of human effect. There is another demonstration of human shape from shading, which is a multi-billion dollar industry. And that's called makeup. So and there's no way to say this without being gender specific, so I will say it. As many women know, properly applied foundation can cause the shape of your cheekbones and other parts of your face and other elements to be perceived as having either a higher shape or more rounded. And what you're doing is you're changing the shading just a little bit so that the human vision system ascribes a slightly different shape to the underlying contour. And so it's taking advantage of shape from shading. And, you know, good makeup artists know exactly how that works. And that's an interesting shading phenomenon. That really ends our conversation about shape from shading. I'll say that, as I said, that lightness, it's still a pretty undersolved problem. Back in the 70s and 80s, where the view that the primary job of vision, or one of the primary jobs of vision, was to reconstruct geometry, there was a lot of focus on how geometry reflected itself in lightness and to try to undo that process. Remember, I talked about vision as being sort of inverse graphics. that whole focus has diminished quite a bit. And the other thing is the idea of being able to take derivatives in images with our current imaging systems where things are, very, all sorts of noise and kinds of things like that. It just was yielding very brittle kinds of results. And likewise, the types of assumptions we had to make were sort of overly restrictive. So I don't think my colleagues would disagree. It says we basically can't do that right now. Okay, so you show us a nice, my coat lying over there. You guys can't see it, the chair, et cetera, whatever. I can tell a lot of shading information by integrating many multiple cues. And we don't really have good techniques for doing that. There is a question of whether machine learning is actually at play. That is, maybe our system doesn't actually undo the physics of the image formation, but instead it has learned the relationship between certain image patch appearance and shape, and it just does that recognition or that mapping without undoing the physics. I would say the jury is still out on that, and probably the truth is going to be somewhere in between. I mean, Ted Adelson's demonstrations of that shadow casting, clearly there's a global effect on sort of a local process, and exactly how we do that is still unknown. So shape from shading is a very old problem, but we could probably use some very new solutions. But now at least you have some idea of the sort of the nature of the problem and what we have done.
Thank you.